What if the entire universe, from the vastness of galaxies to the beating of your own heart, depended on a handful of numbers so small they are almost impossible to imagine? Numbers like the mass of an electron, the strength of gravity, or the precise charge of a proton. On the surface, they seem arbitrary, almost random, as if someone just dialed them in without a second thought. But what if these tiny values aren't accidents at all? What if they're actually profound clues, hidden messages woven into the very fabric of reality that point towards something deeper, something unified, something breathtakingly grand? These numbers are what physicists call fundamental constants. They appear in the equations that govern everything from the behavior of atoms to the expansion of the cosmos, and they never change. They're the fixed points in the swirling chaos of existence, the silent rules that make our universe what it is. And here's what's truly mind-bending. If any one of them were even slightly different, stars wouldn't shine, planets wouldn't form, and life as we know it would be impossible. It's as though the universe has been perfectly tuned, and these minuscule numbers are the tuning knobs. But who or what is doing the tuning? In this video, we're going to explore why these smallest numbers in physics might be our most important guides to understanding reality itself. We'll journey from the quantum realm, where particles flicker in and out of existence, to the cosmic scale, where galaxies rush apart in the dark. Along the way, we'll see how these values bridge the gap between the very small and the unimaginably large, offering hints about the Big Bang, the nature of dark energy, and even the possibility of other universes. This isn't just a story about math or science, it's a detective story, one where the clues are written in the language of the cosmos, and the mystery is nothing less than why anything exists at all. So join us as we unravel these enigmas and discover how the tiniest numbers might just hold the keys to the largest truths. Think of the universe as the most complex machine ever built, a cosmic engine with countless moving parts. But unlike any machine we could invent, it runs on a set of immutable rules, a fixed and unchanging code. This code is written not in ones and zeros, but in a series of fundamental constants. These are the numerical values that appear in the deepest laws of physics, the bedrock numbers that everything else is built upon. They are the universe's non-negotiable terms and conditions. The speed of light in a vacuum, often denoted by the letter c, is exactly 299,792,458 meters per second. Planck's constant, h, which governs the quantum world, is a minuscule 6.626 times 10 to the negative 34th joule-seconds, and the gravitational constant, g, which tells us the strength of the pull between masses, is 6.674 times 10 to the negative 11th Newton-meters squared per kilogram squared. These aren't numbers that scientists calculated from first principles. They are values that had to be painstakingly measured through experiment and observation. They are discovered, not invented, and their precision is absolutely terrifying. If the speed of light were even a fraction different, the relationship between energy and matter would break down. If Planck's constant were altered, the stability of atoms would vanish. The gravitational constant dictates the very architecture of the cosmos, from the orbits of planets to the formation of galaxies. These values are so precise and so crucial that physicists often use a powerful metaphor. They are the dials on the control panel of the universe, and as far as we can tell, every single one of these dials is set to an exquisitely specific value that allows for the existence of complex structures, chemistry, and ultimately, us. The history of measuring these constants is a story of humanity's growing ambition to understand the cosmos. In the late 18th century, scientist Henry Cavendish performed a brilliant experiment with lead spheres and a torsion balance to measure the gravitational constant for the first time, giving us a glimpse into the strength of the force that holds the cosmos together. Later, Max Planck's work on blackbody radiation revealed a fundamental unit of action, a quantum of energy that opened the door to an entirely new field of physics. And of course, Albert Einstein's theory of special relativity placed the speed of light as the ultimate speed limit of the universe, an unchanging constant against which all motion is measured. Today, our measurements have become astonishingly precise. Laboratories around the world use advanced lasers, atomic clocks, and intricate interferometers to pin down these values to more and more decimal places, searching for any hint that they might not be constant after all. This raises two profound and haunting questions that have puzzled physicists for decades. First, why do these constants have the specific values that they do? Is there a reason, a deeper law that dictates why the speed of light is what it is and not something else? Or are we simply left to accept them as brute facts of existence? Second, are they truly constant? Have they always been the same since the first moment of the Big Bang? And are they the same in every corner of the universe? Or could they slowly change over billions of years or vary across unimaginable distances? The answers to these questions might be the most important clues we have in our quest to understand the larger reality behind the curtain of our everyday experience. Now, take that idea of a cosmic control panel with its dials set to specific values and push it one step further. What if those dials weren't just set to any random position, but were adjusted with a precision that defies belief, all to make our existence possible? This is the heart of the fine-tuning problem, a concept so startling that it forces us to confront the very nature of our universe. It's the realization that the fundamental constants don't just have values, they have the right values. If any one of them were even minutely different, the universe would be a vast, empty, and lifeless void. There would be no stars, no planets, no chemistry, and certainly no one around to wonder about it all. Consider the force of gravity described by that gravitational constant. If it were even slightly stronger, the consequences would be catastrophic. Stars would collapse under their own weight much more quickly, burning through their nuclear fuel at a ferocious rate. A star like our Sun might last only a few million years instead of billions, snuffing out any chance for life to evolve on orbiting planets. On the other hand, if gravity were just a bit weaker, it would never be strong enough to pull clouds of gas and dust together to form stars in the first place. Galaxies would never coalesce, and the cosmos would remain a thin, dark, and formless haze of hydrogen. The strength of gravity sits in a breathtakingly narrow Goldilocks zone, not too strong, not too weak, but just right for a universe full of structure and light. This exquisite sensitivity isn't limited to gravity. Look at the strong nuclear force which glues protons and neutrons together inside atomic nuclei. If this force were a little weaker, it couldn't overcome the repulsive electric force between positively charged protons. Simple hydrogen would be the only element that could exist, and the complex atoms necessary for life, carbon, oxygen, nitrogen, would never be forged in the hearts of stars. The periodic table would be a blank page, but if the strong force were slightly stronger, two protons could bind together directly without the need for neutrons. This would cause all the hydrogen in the early universe to fuse into heavier elements almost instantly, leaving no fuel for stars to ever ignite. Once again, the dial for this force is set to a value that allows for a rich chemistry and a long-lived, star-filled cosmos. Perhaps the most famous example of this fine-tuning is the cosmological constant, the number that represents the energy of empty space and drives the accelerating expansion of the universe. The value we observe is positive but incredibly small. If it were significantly larger, even by a factor of 10, the accelerated expansion would have begun so early and so violently that galaxies and stars would never have had time to form. The universe would have been ripped apart before it could even get started. The precision required here is almost incomprehensible. Theoretical physicist Steven Weinberg noted that the acceptable range for this constant is astonishingly narrow. A change by even 1 part in 10 to the power of 120 would render the universe lifeless. That's a 1 with 120 zeros after it, a number so vast it exceeds the number of atoms in the observable universe. The odds of landing on the right value by chance seem infinitesimally small. This overwhelming evidence for fine-tuning has led physicists to propose some truly mind-bending explanations. The renowned cosmologist Martin Rees, the astronomer royal, formalized one line of reasoning with the anthropic principle. In its simplest form, it states that the constants must be compatible with the existence of observers because we are here to observe them. It's a statement of selection bias. We shouldn't be surprised to find ourselves in a universe that allows for our existence, even if such a universe is incredibly rare. This principle doesn't explain why the constants are right. It just notes that we couldn't be anywhere else. For some, this statistical observation points toward the existence of a multiverse, a vast, perhaps infinite, ensemble of universes, each with its own random set of physical constants. In this grand cosmic landscape, most universes are stillborn or barren, but in a tiny, lucky fraction, the numbers line up perfectly and life emerges. We simply find ourselves in one of those fortunate few. It's a compelling idea, but it raises its own questions. If other universes exist, can we ever detect them? Is this a testable scientific theory or merely a philosophical escape hatch? Others see the fine-tuning as potential evidence for design, a universe crafted with intention. Yet another camp holds out hope that a deeper, more fundamental physical theory, a true theory of everything, will eventually reveal that these constants aren't free parameters at all. They might be the inevitable outcome of a single, elegant equation, leaving no room for chance or choice. The values would be what they are because they must be, derived from a higher mathematical necessity we have yet to discover. So where does that leave us? Are we the product of unimaginable luck in a single universe, one member of a vast cosmic family, or the intended outcome of a deeper law? The fine-tuning problem doesn't provide easy answers, but it frames one of the most profound questions we can ask. It challenges us to look at the smallest numbers in physics not as arbitrary details, but as the most significant clues we have about the true nature of reality. But if the fundamental constants are the universe's finely tuned dials, then gravity is the one dial that seems to be turned down so low it's almost off. This brings us to one of the most persistent and puzzling mysteries in all of theoretical physics, the hierarchy problem. At its core, this problem asks a deceptively simple question. Why is gravity so unbelievably weak compared to every other force in nature? Think about it for a second. A tiny refrigerator magnet powered by the electromagnetic force can overcome the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons. That's like a single whisper holding its own against a thunderous orchestra playing at full volume. The numbers themselves tell a shocking story. The gravitational force between two electrons is a staggering 10 to the power of 42 times weaker than the electromagnetic force pushing them apart. That's not just a small difference, it's a chasm of incomprehensible scale. This immense weakness is encoded in the tiny value of the gravitational constant, g. But for physicists, this isn't just a curiosity. It's a profound crisis for our theories. When we try to unify gravity, described by Einstein's general relativity, with the quantum world of the other forces, this disparity blows up in our faces quite literally. The problem becomes crystal clear when we look at two fundamental energy scales in physics. First, there's the electroweak scale. This is the energy at which the electromagnetic and weak nuclear forces merge into a single electroweak force, and it's about 246 gigaelectronvolts. This is the energy realm of the Large Hadron Collider and the Higgs boson. Then there's the Planck scale. This is the energy at which gravity is expected to become as strong as the other forces and quantum effects must dominate. It is a numbing 10 to the power of 19 gigaelectronvolts. The sheer gap between these two scales is the hierarchy problem in a nutshell. Why are these two fundamental benchmarks separated by 16 orders of magnitude? It's as if the fundamental rules of reality have two completely different sets of instructions for how strong forces should be, and no one knows why. This isn't just an aesthetic issue, it points to a deep instability in our models. In quantum field theory, the mass of particles like the Higgs boson receives corrections from its interactions with every other particle in the universe. These quantum fluctuations should, in theory, drive the mass of the Higgs and by extension the electroweak scale, all the way up to the enormous Planck scale. For the math to work out and give us the weak universe we actually observe, these enormous quantum contributions must cancel each other out with a precision that looks like a miracle. It requires a fine-tuning that makes many physicists deeply uncomfortable, suggesting that our current picture is incomplete. This is where the search for new physics begins. The most prominent proposed solution is a beautiful symmetry known as supersymmetry. This theory postulates that every known particle has a hidden superpartner twin. For every electron, there would be a selectron, for every quark, a squark. The magic of supersymmetry is that the quantum contributions from these superpartners would perfectly cancel out the problematic corrections that blow up the Higgs mass, naturally stabilizing the hierarchy. It elegantly explains why the electroweak scale remains small and separate from the Planck scale. There's just one catch: we haven't found any of these superpartner particles yet. Experiments at the Large Hadron Collider have been searching for them, and so far, the universe hasn't obliged, forcing physicists to tweak the theory and consider other, even more exotic possibilities. Another compelling idea is that gravity only appears weak because it is literally leaking into other dimensions. In some brainworld scenarios, our entire universe of 3 spatial dimensions could be a membrane floating within a higher dimensional space. The other forces, electromagnetism and the nuclear forces, are stuck to our brain, which is why they appear strong to us. But gravity, which governs the shape of space-time itself, can seep out into these extra dimensions. Its strength would be diluted across a much larger volume, explaining why it feels so faint from our limited, 3-dimensional perspective. In this view, the small value of the gravitational constant isn't a fundamental property of gravity itself, but merely an artifact of our parochial viewpoint within a much larger, higher-dimensional reality. The hierarchy problem, then, transforms from a puzzle about numbers into a potential clue about the true, hidden architecture of the cosmos, hinting that the dimensions we experience are just a fraction of the whole. And yet, even the immense weakness of gravity pales in comparison to the profound smallness of another number, one that represents perhaps the greatest mismatch between theory and observation in the entire history of science, the cosmological constant. Denoted by the Greek letter lambda, this is not a force but a property of space itself, the energy density of the vacuum, the latent energy hidden in what we perceive as nothingness. Its story begins not with a discovery but with a retraction. When Albert Einstein was formulating his theory of general relativity, his equations suggested a universe that should be either expanding or contracting. Believing, like most astronomers of his time, in a static and eternal cosmos, he introduced the cosmological constant as a kind of mathematical fudge factor, a repulsive force that would precisely counterbalance the attractive pull of gravity and keep the universe perfectly still. He would later call this his greatest blunder, after Edwin Hubble's observations confirmed the universe was indeed expanding. For decades, lambda was set to zero and largely forgotten, a relic of a mistaken assumption. But then, in the late 1990s, two separate teams of astronomers made a discovery that would turn cosmology on its head. By observing distant supernova, they found that the expansion of the universe wasn't slowing down, as everyone expected due to gravity's relentless pull. It was speeding up. Something was pushing galaxies apart with ever-increasing force. That something was given a name, dark energy, and the simplest, most elegant explanation for it was the sudden and dramatic resurrection of Einstein's cosmological constant. It wasn't a blunder after all, it was a prediction. The vacuum of space, it turns out, isn't empty. According to quantum field theory, it is a seething, bubbling foam of virtual particles constantly flickering in and out of existence. This quantum frenzy should be filled with an enormous amount of energy. When physicists try to calculate how much energy this quantum vacuum should have, they do so by summing up all the contributions from every possible quantum fluctuation, all the way down to the Planck scale. The answer they get is staggering. The theoretical prediction for the value of the cosmological constant is roughly 120 orders of magnitude larger than the value we actually observe. To put that number in perspective, 10 to the power of 120 is a 1 followed by 120 zeros. It is a number so vastly larger than the number of atoms in the observable universe that it defies any human analogy. The predicted value is essentially the largest number you can get from fundamental physics, but the observed value, the one measured by our most powerful telescopes, is not just a little smaller. It is almost zero. It is a tiny, positive number that causes the universe to accelerate at exactly the rate we see. This is the cosmological constant problem in its full, terrifying glory. It is the worst prediction in all of physics. Why is the energy of the vacuum so much smaller than it has any right to be? Why isn't this immense vacuum energy tearing the fabric of space-time apart? The problem is so severe that the Nobel laureate Steven Weinberg once remarked that it presents a fundamental challenge to our understanding of the natural world, suggesting that we are missing a crucial piece of the puzzle. He, along with others, proposed a radical solution rooted in the anthropic principle. In a vast multiverse where the value of the cosmological constant varies randomly from one universe to the next, only those universes with a value extremely close to zero would be capable of forming galaxies, stars, and planets. In universes with a larger positive value, the repulsive force would be so powerful that it would rip everything apart before any structure could form. In universes with a large negative value, the universe would collapse in a big crunch almost instantly. We, of course, find ourselves in one of the rare habitable universes where the number is almost zero, not because of any fundamental law, but simply because it's the only kind of universe we can inhabit. This tiny, non-zero value doesn't just make our existence possible, it dictates the ultimate fate of everything. That faint, relentless push of dark energy is now the dominant force in the cosmos, governing its long-term evolution. It is leading us toward a future known as the heat death, where the universe continues to expand and accelerate forever. galaxies flying apart until each star system is isolated in an ever-cooling, ever-darkening void. The cosmological constant, this smallest of numbers, is the author of that final, silent chapter. Its inexplicable value is a constant reminder that our most successful theories are still incomplete, a whisper from the vacuum that there are deeper truths about reality waiting to be uncovered. While the cosmological constant deals with the vast emptiness of space, another small number governs the very building blocks of matter right here on Earth. Consider the proton and the electron, two fundamental players in the atomic world. The proton sits heavily in the nucleus while the electron zips around it in a cloud. Their masses are vastly different, and the ratio between them is a fixed, dimensionless number that has been measured with incredible precision. A proton is approximately 1,836 times heavier than an electron. This isn't just a random piece of trivia. This number, 1,836, is one of the most important unsung heroes in the universe. It is a silent architect of reality as we know it. The significance of this ratio becomes breathtakingly clear when we play the what-if game. What if the proton were only, say, 10 times heavier than the electron instead of nearly 2,000 times? In that altered universe, the delicate dance of atomic bonding would fall into chaos. The proton's greater mass is what keeps the atomic nucleus relatively stable and anchored. If it were too light, the quantum jostling within the nucleus would make it far less secure, potentially destabilizing the very elements that make up our world. Conversely, if the proton were even heavier relative to the electron's orbit would shrink dramatically. Atoms would become incredibly tiny and cramped. This change would utterly wreck the complex patterns of chemical bonding, the elegant rules of chemistry that allow for the vast diversity of molecules. From simple water to complex DNA rely entirely on the specific sizes and energy levels of electron orbitals. Tweak the proton-electron mass ratio and you alter the entire periodic table. Carbon atoms might not be able to form the long chains necessary for life. Water might not have the unique properties that make it such a fantastic solvent. The intricate machinery of proteins and enzymes would simply fail to assemble. Life in any form we can recognize would be an impossibility. This one number acts as a master key, unlocking the potential for complexity and chemistry in our cosmos. But where does this precise and crucial value come from? This is where the mystery deepens. The mass of the electron is believed to come from its interaction with the Higgs field, a fundamental process. But the proton's mass is a different story altogether. A proton isn't a fundamental particle. It's a messy composite object made of three quarks bound together by the strong nuclear force, which is described by a theory called quantum chromodynamics. The astonishing thing is that the sum of the masses of those three quarks accounts for only about 1% of the proton's total mass. The other 99% comes from the pure energy of the gluons, the force carriers of the strong interaction, and the frenetic motion of the quarks themselves, all confined within a tiny volume. So, the proton-electron mass ratio isn't a simple number derived from first principles. It emerges from the complex, dynamic, and still not fully understood interactions of quantum chromodynamics. Our theories can use supercomputers to calculate this ratio from the theory's equations, and they get it roughly right, which is a triumph. But we cannot yet look at the fundamental laws and predict that the number must be 1,836. It is a value that the universe has, and we must accept it as a given. This very mystery captivated some of the greatest minds of the 20th century. The renowned astrophysicist Sir Arthur Eddington, a man who helped prove Einstein's theory of relativity, became obsessed with fundamental numbers late in his career. He was particularly fascinated by the fine structure constant, but he also saw profound significance in the ratio of the proton mass to the electron mass. Eddington embarked on a long and lonely quest to derive these constants from pure thought and fundamental theory, often working with numerological formulas that many of his colleagues dismissed as mystical speculation. While his specific mathematical attempts are not considered valid science today, his deep intuition that these numbers must hold a deeper meaning continues to resonate. He believed they were clues pointing toward a more complete and unified understanding of physics, one that would seamlessly connect the quantum world with the cosmos. So we are left to wonder, is the proton-electron mass ratio simply a random outcome of how the universe cooled after the Big Bang, a frozen-in accident of cosmic history? Or is it, as Eddington felt, a profound signpost pointing toward a hidden symmetry or a deeper layer of physical law that we have yet to uncover? This one small number, so critical for the existence of molecules, planets, and people, remains a beautiful and stubborn puzzle. It is a powerful reminder that the stability of the very matter we are made of depends on values that we can measure with exquisite precision but cannot yet truly explain. But if the proton-electron mass ratio is a crucial architect of matter, then the fine structure constant is the master conductor of light and energy itself. Denoted by the Greek letter alpha, this number is approximately 1 divided by 137, a value so seemingly insignificant that it's easy to overlook. Yet, this humble fraction is arguably the most famous and mysterious dimensionless constant in all of physics. It is a pure number, a ratio that has no units, which means its value is the same whether you're measuring in inches or light years, on Earth or in a distant galaxy. It defines the strength of the electromagnetic force, governing how tightly electrons are bound to atomic nuclei, how atoms absorb and emit light, and how energy is exchanged in every chemical reaction that has ever occurred. The influence of alpha is absolutely everywhere. When sunlight streams through a droplet of water and creates a rainbow, the specific colors and their precise wavelengths are a direct fingerprint of the fine structure constant. The vibrant red of a neon sign and the unique green of a copper flame are all orchestrated by this number. It is woven into the very fabric of atomic spectra, the barcodes that allow astronomers to identify the composition of stars billions of light years away. In the realm of chemistry, it dictates the strength of the bonds that hold molecules together. If alpha were even a few % larger, the electromagnetic force would be stronger, pulling electrons much closer to the atomic nucleus. Atoms would shrink, and their ability to share electrons and form stable, complex molecules would be severely compromised. The intricate dance of life, built on a foundation of precise molecular interactions, would likely be impossible. Conversely, if alpha were smaller, the force would be weaker. Atoms would become bloated and unstable, unable to hold onto their electrons, and the orderly structure of matter would dissolve into a chaotic soup. This profound fine-tuning is why physicists have been both captivated and confounded by this number for over a century. The legendary Richard Feynman, one of the greatest theoretical minds of the 20th century, called it one of the greatest damn mysteries of physics. He famously said, "All good theoretical physicists put this number up on their wall and worry about it. It's a magic number that comes to us with no understanding. We know what kind of a dance to do to measure it to a very high degree of accuracy, but we don't know what kind of dance to do on a computer to make it come out. We cannot derive it from any fundamental theory. It is an input to our equations, not an output. This has led to countless attempts to crack its code. For some, its dimensionless nature suggests it might be a key that unlocks a deeper level of reality, a bridge between the quantum world and the cosmos. This mystery has inspired not just scientific inquiry but a touch of the mystical. The number 137 held a particular fascination for Wolfgang Pauli, a pioneer of quantum physics known for his sharp intellect and his so-called Pauli effect, where equipment would allegedly malfunction in his presence. Pauli became obsessed with the fine structure constant and the number 137. He reportedly joked that if God allowed him to ask one question after death, it would be, why 1 divided by 137? Ironically, Pauli died in hospital room number 137, a coincidence that has fueled the number's legendary status among physicists. While this is a poignant anecdote, it underscores the deep, almost philosophical hold this number has on those who study it. The quest to understand alpha continues to drive modern science. Some researchers, inspired by ideas from string theory or other attempts at a theory of everything, have proposed formulas that might derive alpha from mathematical constants like pi. Others have wondered if its value could be changing imperceptibly over cosmic time, a possibility that teams of astronomers are actively testing by comparing the light from incredibly distant quasars to lab measurements. So far, the constant has remained constant, but the search itself reveals how a single, small number can sit at the very heart of our understanding, connecting the behavior of a single electron to the grand evolution of the entire universe. It is a perfect example of how the deepest clues about reality are often hidden not in complex equations, but in the simplest, most elegant, and most inexplicable of numbers. Yet for all its cosmic importance, the gravitational constant, known simply as G, remains one of the most stubbornly elusive numbers to pin down in all of experimental physics. While the speed of light in a vacuum is now defined with absolute precision and Planck's constant is known to many decimal places, G is still measured with a frustrating degree of uncertainty. Its accepted value has a relative standard uncertainty that is thousands of times larger than that of any other fundamental constant. This isn't for a lack of trying. It's because gravity in the everyday world of a laboratory is incredibly and almost absurdly weak. The gravitational pull between two objects you can hold in your hands is so infinitesimal that it is drowned out by the slightest environmental noise, a passing truck, a subtle temperature change, even the seismic vibrations from waves crashing on a distant shore. Measuring G is like trying to hear a single, quiet note played in a symphony hall during a thunderstorm. This epic struggle for precision began in earnest at the end of the 18th century with a brilliant and famously reclusive scientist named Henry Cavendish. His experiment was a masterpiece of ingenuity. He took a 6-foot wooden rod and attached a pair of small lead spheres to each end, suspending this entire apparatus from a thin wire to create an incredibly sensitive torsion balance. Then he brought two larger, 300-pound lead weights close to the smaller balls. The faint, almost imperceptible gravitational tug between the large and small weights caused the wire to twist by a minuscule amount. By meticulously measuring this tiny twist with a beam of light reflected off a mirror, Cavendish was, for the first time in history, able to weigh the Earth, calculating its density and providing the first real measurement of G. His setup was so sensitive that it is still known today as the Cavendish experiment. In the centuries since, physicists have refined this basic design with lasers, advanced materials, and vacuum chambers, attempting to isolate their experiments from any possible disturbance. They've used everything from metal pendulums to floating magnets in liquid helium. Yet, perplexingly, the results from the world's top laboratories stubbornly refuse to agree with each other. The latest values published by teams in the United States, China, and Europe, while incredibly close, still disagree by more than their estimated margins of error. This suggests there is a source of uncertainty, a hidden variable or a subtle systematic effect that we still do not understand or cannot control. It is a humbling reminder that for all our technological prowess, the quietest force in the universe still guards its secrets closely, demanding a level of precision that continues to push the boundaries of human ingenuity. This ongoing challenge leads to a profound and radical question. What if the discrepancies aren't just due to experimental error? What if the gravitational constant isn't actually constant at all? The idea that G could vary over time or across space is not just science fiction. It's a serious proposal that has emerged from several attempts to unify gravity with the other forces. In some extensions of Einstein's theory, the value of G could have been different in the extremely early universe, slowly settling into its present value as the cosmos cooled. Other theories, like those involving extra dimensions, suggest that what we perceive as G might not be a fundamental property, but an emergent one that could change depending on the local environment. If true, the implications would shake cosmology to its core. The entire history of the universe, from the rate of its initial expansion to the age we calculate for it, is built upon the assumption that G has always been what we measure it to be today. If that foundation were shown to be shifting sand, we would have to rewrite our understanding of cosmic evolution. So this small number, so difficult to measure on a lab bench, represents so much more than just the strength of a force. It is a test of our fundamental assumptions about reality. It is a puzzle that connects the most delicate human experiments to the grandest scales of the cosmos. The quiet force of gravity, which silently sculpts galaxies and holds planets in their orbits, continues to speak in a whisper, challenging us to listen just a little more carefully, to be a little more precise, and to remain open to the possibility that even our most deeply held constants might still have a story left to tell. Now, if the gravitational constant G represents the quiet strength of the cosmos, and the fine structure constant alpha conducts the symphony of light, then the Planck scale is the universe's ultimate backstage pass, a realm of such profound smallness that it redefines our very notions of space, time, and reality itself. This isn't just another set of tiny numbers, it is the final frontier of the infinitesimal, a domain where our current laws of physics break down and something entirely new must take over. The Planck scale is not something we can measure directly. It is derived by combining nature's most fundamental constants in just the right way. By mixing the gravitational constant G, the speed of light c, and Planck's constant h, we can construct units of length, time, and mass that are, in a deep sense, the most natural units possible. They are completely free from any human-centered bias like the meter or the second, which were based on the size of the Earth or the length of a day. These are the units that the universe itself uses in its deepest code. The numbers that emerge are almost impossible to truly grasp. The Planck length is about 10 to the negative 35 meters. To say this is small doesn't even begin to cover it. If you were to magnify a single atom to the size of the entire observable universe, the Planck length would be roughly the height of an average tree. It is the smallest possible unit of distance that has any physical meaning. Similarly, the Planck time is how long it takes light to travel that minuscule distance, a fleeting 10 to the negative 43 seconds. This is to 1 second what 1 second is to hundreds of trillions of times the current age of the universe. And the Planck mass, while still tiny at about 22 micrograms, is surprisingly hefty compared to a proton. It's about the mass of a fine grain of sand, but packed into a space 100 trillion times smaller. This bizarre combination of incredible density and unimaginable smallness hints at the violent, chaotic quantum gravity that must dominate at this scale. This is the scale where the smooth, geometric landscape of Einstein's general relativity collides head-on with the fuzzy, probabilistic world of quantum mechanics. In our everyday experience, space appears continuous and infinitely divisible, but the Planck scale suggests this is an illusion. The visionary physicist John Wheeler proposed that if we could peer down to this level, the fabric of spacetime would not be smooth and serene. Instead, it would be a chaotic, seething foam, a turbulent ocean of virtual particles and miniature black holes constantly popping into and out of existence. In this quantum foam, the very concepts of before and after, or here and there, become meaningless. Distances and durations fluctuate wildly, and the idea of a predictable, causal universe dissolves into a probabilistic frenzy. This isn't just theoretical speculation. It presents a concrete solution to a major conflict. General relativity describes gravity as the curvature of a smooth spacetime continuum, while quantum mechanics demands that everything, including spacetime itself, must be subject to uncertainty and quantization. The Planck length is the point where the curvature of space becomes so extreme that it must be grainy, resolving the paradox by revealing that spacetime itself is made of discrete, fundamental units. This idea of a discrete spacetime is at the heart of several approaches to quantum gravity, like loop quantum gravity and string theory. They suggest that just as matter is made of atoms, space itself may be composed of tiny, indivisible units of volume, a pixelated reality at the most fundamental level. This isn't just a philosophical curiosity. It has potential experimental consequences. Some theories predict that this foamy structure could subtly alter the speed of very high-energy light traveling across the universe, or it could cause ultra-precise atomic clocks to desynchronize in unpredictable ways. While we are still far from being able to probe the Planck scale directly with experiments, its existence as a fundamental limit shapes our theoretical pursuits. It tells us that the universe has a built-in resolution, a point beyond which the zoom function simply stops working. The extreme smallness of the Planck units isn't a quirk. It is a profound clue that we are brushing up against the ultimate limits of physical reality, a domain where a deeper, more unified theory must emerge to describe the cosmos not as we perceive it, but as it truly is. But to truly grasp how the universe arrived at the constants we see today, we must rewind the cosmic clock to a fraction of a second after the beginning, to an event of unimaginable violence and expansion, cosmic inflation. This theory proposes that the universe underwent a breathtakingly brief, exponential growth spurt, doubling in size over and over again in a span of time so short it makes a blink look like an eternity. And the engine of this incredible expansion, the inflattened field, was governed by parameters so exquisitely small and finely tuned that they make the cosmological constant seem almost coarse by comparison. The problem's inflation was invented to solve our fundamental puzzles about the universe's very structure. The first is the horizon problem. When we look at the cosmic microwave background radiation, the ancient afterglow of the Big Bang, we see a sky that is almost perfectly uniform in temperature. Regions on opposite sides of the sky are identical to 1 part in 100,000, a stunning level of consistency. But according to the standard Big Bang model, these regions were never in causal contact. Light simply hasn't had enough time to travel between them since the universe began. It's as if thousands of people in a vast, crowded room who have never spoken or signaled to each other are all wearing the exact same outfit. How did they all coordinate? Inflation provides the answer. Before this rapid expansion, the entire observable universe was a tiny, subatomic patch that was in perfect thermal equilibrium. Inflation then took this tiny, uniform region and stretched it to a size larger than our entire visible cosmos. preserving that smoothness while pushing any remaining wrinkles far beyond the horizon. The entire sky looks uniform because it all came from a single, minuscule, and coherent piece of the early universe. The second puzzle is the flatness problem. Our measurements tell us that the universe is geometrically flat to an astonishing degree of precision. This means that the density of matter and energy is almost exactly at the critical value that balances the expansion against the pull of gravity. But in the Standard Model, any slight deviation from perfect flatness in the early universe would have been wildly amplified over billions of years. For the universe to be as flat as it is today, its density at 1 second after the Big Bang had to be fine-tuned to within 1 part in 10 to the power of 15. That's like balancing a pencil on its tip with such precision that it's still standing over 14 billion years later. Inflation acts like a cosmic iron, stretching the fabric of spacetime so dramatically that any initial curvature is smoothed out to near perfection. No matter how curved or wrinkled your starting point, if you inflate a balloon to an enormous size, the surface of your little patch will appear incredibly flat. But for this elegant solution to work, the inflattened field itself had to possess very specific and very small properties. This is where the numbers come in. The theory requires that the field's potential energy curve be extremely flat, a condition physicists call slow roll. Imagine a bowling ball rolling down a long, almost perfectly flat hill. If the hill is too steep, the ball will accelerate quickly and crash at the bottom, ending inflation too abruptly. But if the hill has just the right, almost imperceptible slope, the ball will roll very, very slowly. During this slow roll, the energy density of the field remains nearly constant, acting like a super-powered version of the cosmological constant and driving the exponential expansion. The parameters that describe this flatness, known as the slow roll parameters, must be very, very small, much less than 1. This incredible fine-tuning is necessary to produce the correct amount of expansion and to generate the tiny quantum fluctuations that later seeded all the galaxies and cosmic structure we see. The energy scale of this inflation is another incredibly small number when viewed from our human perspective, yet it is enormous in the context of particle physics. It is typically around 10 to the power of 16 gigaelectronvolts, which is a millionth of a Planck energy. This places it tantalizingly close to the energy scales associated with grand unified theories, suggesting that inflation might not be an isolated event, but a direct consequence of the fundamental forces of nature merging into one. The fact that these parameters are so small and so precise is not seen as a weakness of the theory by most cosmologists, but rather as a powerful clue. Such exquisite fine-tuning often points toward a deeper underlying mechanism. Perhaps the inflattened field is not a random add-on but emerges naturally from a more complete theory like string theory, where the flatness of its potential is protected by a fundamental symmetry. Or perhaps the small numbers are a sign that our universe is just one bubble in a vast multiverse, a cosmic landscape where only universes with the right parameters for inflation, and thus for life, can form. In this way, the incredibly small numbers that drove the universe's first explosive moments are directly connected to the constants we measure today, weaving a single thread from the quantum dawn of time to the vast, structured cosmos we call home. While the Planck scale takes us to the very edge of reality and inflation rewinds us to the universe's first moments, there is another profound mystery hiding in plain sight, one that involves particles so light they almost don't exist at all. These are neutrinos, the ghosts of the particle world. Billions of them are passing through your body every second, emanating from the sun, from distant supernova, and even from the Big Bang itself. Yet they interact with matter so rarely that they leave almost no trace. For decades, the standard model of particle physics, our most successful catalog of the fundamental building blocks of the universe, assumed these particles were utterly massless, just like the photon. But nature, as it often does, had a surprise in store. We now know that neutrinos do have mass, but it is an almost impossibly small amount, less than 1/1,000,000th the mass of an electron, the next lightest particle. This tiny mass is not just a curious detail, it is a glaring anomaly, a crack in the foundation of our most cherished theories, and it points toward a reality far larger and more exotic than we ever imagined. The first clue that something was strange with neutrinos came from a problem deep underground. In the 1960s, physicist Raymond Davis Jr. set up an experiment in the Homestake gold mine in South Dakota to count the number of neutrinos arriving from the sun. His results were baffling. He was detecting only about 1/3 of the number predicted by solar models. This was the famous solar neutrino problem, and for decades it remained an unsolved puzzle. Were our models of the sun wrong, or was our understanding of neutrinos incomplete? The answer came from a monumental experiment in Japan known as Super Kamiokande, a massive detector filled with 50,000 tons of ultra-pure water, buried a kilometer beneath a mountain to shield it from cosmic rays. Here in the late 1990s, a team led by researchers like Yoichiro Suzuki observed something extraordinary. Neutrinos were changing their identity. As they traveled through space, a neutrino born in the sun as one flavor, the electron neutrino, could spontaneously transform into a muon or tau neutrino, a different flavor that Davis's experiment was not designed to detect. This phenomenon, called neutrino oscillation, was the smoking gun. The very fact that neutrinos can oscillate, that they can change from one type to another as they travel, is direct, undeniable proof that they must have mass. It's a quantum mechanical effect that is only possible if the different neutrino types have slightly different masses. This discovery was so monumental that it earned the leaders of the Super K team the Nobel Prize in Physics in 2015. But this revelation immediately created a new and deeper puzzle. Why is their mass so vanishingly small? In the standard model, particles get their mass from interacting with the Higgs field. The stronger the interaction, the heavier the particle. This works beautifully for particles like the top quark, which has a tremendous interaction with the Higgs, and even for the electron. But the neutrino's interaction is so weak that it is effectively zero. It's as if the neutrino is barely paying attention to the Higgs field at all. This isn't just a small adjustment, it's a complete departure from the rules. To explain this, physicists have had to propose some of the most daring ideas in modern science. The leading theory is called the seesaw mechanism. This elegant concept proposes that for every familiar, light neutrino we see, there is a monstrously heavy partner neutrino that we have not yet detected. These hypothetical heavy neutrinos could be billions of times more massive than a proton. In this seesaw, the tiny mass of the ordinary neutrino and the enormous mass of its heavy partner are connected. As one goes up, the other goes down. The incredible lightness of our neutrinos is therefore a direct consequence of the incredible heaviness of their hidden partners. This isn't just a clever fix. If true, it would mean that our universe contains entire families of particles operating at energy scales far beyond what our most powerful colliders can reach, hinting at a hidden sector of reality governed by new, profound symmetries. Other theories venture into even more speculative territory, suggesting that the neutrino's minuscule mass could be a sign that it is not a typical particle at all. Some models propose that the neutrino could be a so-called Majorana particle, which is its own antiparticle. This unique property would not only explain its small mass, but could also be the key to understanding one of the universe's greatest mysteries. why there is so much more matter than antimatter. If neutrinos are Majorana particles, a process called leptogenesis could have occurred in the early universe, creating a small excess of matter over antimatter that eventually led to everything we see today. Another radical idea is that the neutrino might not be confined to our three-dimensional space like other particles. Perhaps it can leak into extra, compactified dimensions predicted by string theory. This leakage could effectively dilute its properties, making it appear incredibly light from our limited perspective. The neutrino, then, would be a cosmic traveler, a messenger from higher dimensions. The implications of solving the neutrino mass puzzle are staggering. These barely their particles are relics from the first second after the Big Bang, and their properties are woven into the evolution of the entire cosmos. Their tiny masses influence how structures like galaxies and galaxy clusters form. They played a crucial role in the synthesis of the first elements and continue to shape the explosive deaths of massive stars. As researcher Yoichiro Suzuki has emphasized, understanding neutrinos is not just about completing a table of particles. It is about reading a history of the universe that is written in the faintest of ink. Do these ghostly particles, the lightest of them all, hold the key to discovering new symmetries that unite the forces of nature? Could their mass be a clue that we are living in a universe with more dimensions than we can perceive? The quest to measure the absolute mass of the neutrino is one of the most active frontiers in physics, with experiments like Katrin in Germany using giant spectrometers to hunt for the faintest whisper of mass in the beta decay of tritium. Each new limit they set helps to constrain the theories and guide us toward a larger reality, proving that sometimes the biggest secrets are hidden not in the most massive objects, but in the lightest. Yet even as we grapple with the ghostly masses of neutrinos, another profound puzzle emerges from the very first minutes of creation, one written not in missing particles but in an element we can hold in our hand, lithium. The story of the Big Bang is in many ways a story of elemental cooking. In the first 20 minutes of the universe's existence, the entire cosmos was a searingly hot nuclear furnace, fusing the primordial soup of protons and neutrons into the first atomic nuclei. This process, known as Big Bang nucleosynthesis, produced almost all the hydrogen and helium we see in the universe today, along with trace amounts of heavier elements like deuterium and lithium. The calculations that describe this process are a triumph of modern cosmology. By plugging in the known laws of nuclear physics and the conditions of the early universe, scientists can predict with stunning accuracy how much of each element should have been forged. For hydrogen and helium, the predictions match the observed abundances in ancient stars and primordial gas clouds almost perfectly. It is a resounding confirmation of the Big Bang model. But for one element, the numbers stubbornly refuse to agree. The theory predicts that the Big Bang should have created about 3 times more lithium-7, the most common isotope of lithium, than what we actually observe spread throughout the oldest stars in our galaxy. This discrepancy, known as the cosmological lithium problem, is a small but persistent thorn in the side of cosmology, a quiet reminder that our understanding of the universe's first moments is still incomplete. This isn't a large, glaring error, but a subtle mismatch, a factor of about 3. Yet in the precise world of fundamental physics, where theories are validated by agreements to many decimal places, a factor of 3 is a yawning chasm. The problem hinges on the incredibly specific and small numbers that govern nuclear reaction rates and cross-sections. The amount of lithium-7 produced is exquisitely sensitive to the details of the nuclear chain reaction that builds it. It begins with the fusion of helium-3 and helium-4 nuclei to form beryllium-7, which then captures an electron to become lithium-7. The predicted final abundance depends critically on the precise probability, or cross-section, of each step in this delicate dance. If any one of these nuclear interaction rates is even slightly miscalculated, the entire result can be thrown off. For decades, physicists have suspected that the solution might lie here, in the nuclear data itself. Perhaps our measurements of these crucial cross-sections in Earth-bound laboratories are ever so slightly inaccurate. Maybe there are unknown nuances in how these reactions proceed at the extreme temperatures and densities of the early universe that we fail to replicate in our experiments. Teams have tirelessly remeasured these rates with ever-increasing precision, yet the problem persists, suggesting that the error might not be with our instruments, but with our fundamental assumptions. This is where the plot thickens and the possibilities become truly fascinating. If the nuclear data is correct, then the discrepancy must point to something new and unexpected happening during those first few minutes. Cosmologists like Brian Fields have spent years exploring these tantalizing possibilities. Could there have been an unknown particle or field present that subtly altered the nuclear reactions? One compelling idea involves a theorized particle called the action, which was originally proposed to solve a different problem in quantum chromodynamics. If actions existed in the early universe, they could have drained energy from the nuclear plasma, effectively cooling it down faster than expected and changing the outcome of the nucleosynthesis process. Another radical proposal is that the fundamental constants themselves, like the fine structure constant that governs the strength of electromagnetic interactions, might have been slightly different in the extreme environment of the infant cosmos. A tiny variation could have shifted the reaction rates just enough to resolve the lithium deficit. These are not wild speculations but serious hypotheses that connect this one small numerical disagreement to some of the most profound questions in physics, from the nature of dark matter to the stability of the laws of nature. The cosmological lithium problem is a beautiful example of a great truth in science. The biggest advances often come from the smallest discrepancies. When theory and observation align perfectly, we can be confident in our models, but it is in the tiny cracks, the mismatches of a mere factor of 3, where the potential for revolution lies. This persistent puzzle has driven physicists to re-examine every link in the chain of reasoning, from the most fundamental nuclear physics to the grandest cosmological models. It forces a humility, reminding us that our understanding of the universe, for all its power, is still a work in progress. The ancient lithium atoms in the oldest stars are like cryptic messages from the dawn of time, and their silent testimony continues to challenge us, pushing our experiments to greater precision and our theories to greater creativity in the relentless pursuit of a larger reality. But if the cosmological lithium problem reveals a crack in our understanding of the universe's first moments, then the hierarchy of masses within the standard model of particle physics presents a mystery that is just as deep and far more personal, because it is the reason the very atoms in your body have any substance at all. Imagine for a moment a grand cosmic ladder, a spectrum of mass that stretches across a breathtaking 30 orders of magnitude. On the very bottom rung, we have the photon, the particle of light, which is completely and utterly massless. It zips across the universe at the ultimate speed limit, forever untouched by the Higgs field. Then, just a step above, we find the almost weightless electron and the elusive neutrinos, particles so light they seem to barely participate in the world of mass. Climbing higher, we encounter the up and down quarks that make up protons and neutrons, and then the strange and charm quarks. Finally, near the very top of this immense ladder, we find the behemoth, the top quark. This particle is staggeringly heavy, about 173 times the mass of a proton, or nearly as heavy as an entire atom of gold. To put this in perspective, the difference in mass between the top quark and an electron is greater than the difference in mass between a blue whale and a single proton. This isn't just a spread, it's a chasm of incomprehensible scale, and it begs a fundamental question. Why does nature need such an extreme range of masses, and what sets the value for each individual particle? The answer, according to our current best theory, lies with the now famous Higgs field and its associated particle, the Higgs boson. The Higgs mechanism is often described as a kind of cosmic molasses or a grand social gathering that particles move through. Particles that interact strongly with this field experience more drag, and we perceive that drag as mass. But this elegant explanation immediately presents its own profound puzzle. The Higgs field doesn't dictate the mass of each particle, it merely provides the stage. The actual strength of each particle's interaction with the Higgs field is determined by a separate, seemingly arbitrary number called a Yukawa coupling. Think of it like this: the Higgs field is a uniform, all-pervasive energy field, but each type of particle has its own unique key to interact with it. The top quark has a key that fits almost perfectly, resulting in a tremendously strong interaction and a huge mass. The electron's key is a poor fit, leading to a very weak interaction and a tiny mass. And the photon's key doesn't exist at all. It simply doesn't interact, so it remains massless. Here's the crucial and deeply puzzling part. Within the standard model, these Yukawa coupling values are not explained by any deeper principle. They are free parameters, 18 of them, to be precise, that must be measured by experiment and then simply plugged into the equations. They are inputs to the theory, not outputs. There is no known reason why the electron's coupling should be roughly 0.0000002, while the top quark's is nearly 1. From the perspective of the mathematics, they could have been almost any other set of values. This is profoundly unsatisfying to physicists. A fundamental theory is supposed to explain the universe, not just describe it with a long list of unexplained numbers. This mass hierarchy problem is a constant reminder that the standard model, for all its incredible predictive power, is likely just a piece of a much larger puzzle. The seemingly random values of these couplings, these small numbers that dictate the heft of reality, are perhaps the most important clues we have, pointing toward a deeper, more unified structure underlying the particles we know. The quest to explain this wild disparity has given rise to some of the most ambitious and beautiful theoretical frameworks in modern physics. Grand unified theories, or GUT, propose that at incredibly high energies, the three quantum forces, the electromagnetic, weak, and strong nuclear forces, were not separate at all, but were facets of a single majestic force. In this fiery, early universe, particles that now seem very different, like quarks and electrons, would have been indistinguishable. As the universe cooled, this unified force would have broken into the three forces we see today, in a process similar to how the Higgs field breaks symmetry. Crucially, this breaking could have generated the different Yukawa couplings from a single, more fundamental set of parameters, explaining the mass hierarchy as a natural consequence of cosmic evolution. While we haven't yet found direct evidence for grand unification, its mathematical elegance is a powerful lure. An even more prominent candidate is supersymmetry. This theory posits that every known particle has a hidden superpartner twin, an electron has a selectron, a quark has a squark, and so on. One of the many virtues of supersymmetry is that it can naturally stabilize the Higgs mass against those catastrophic quantum corrections we discussed earlier. But it also offers a potential path to understanding the Yukawa couplings. In a supersymmetric world, the relationships between particles are tightened by a powerful new symmetry. This symmetry could provide a theoretical framework where the values of the couplings are not random, but are instead determined by the underlying geometry of the theory. They might be calculated from first principles, transforming them from arbitrary inputs into beautiful, inevitable outputs. The fact that we have not yet found any of these super-partner particles at the Large Hadron Collider has put significant pressure on the simplest versions of supersymmetry, but the core idea remains a compelling direction for explaining the universe's deepest patterns. Ultimately, the hierarchy of masses is not just a technical detail for physicists to ponder. It is the very foundation of a stable, complex universe. If the up and down quarks were significantly heavier, the proton itself could become unstable, causing all atomic nuclei to disintegrate. If the electron were much heavier, atoms would shrink dramatically, altering all of chemistry beyond recognition. The specific values of these Yukawa couplings appear to be just as fine-tuned as the cosmological constant or the strength of gravity for the existence of life. This has led some to consider, once again, the possibility of a multiverse, a vast landscape of universes where these couplings take on every conceivable value. In most of those universes, the combinations are disastrous and no atoms or stars can form. But in a rare, fortunate subset, the numbers line up perfectly and we find ourselves in one of those cosmic sweet spots. Whether the answer lies in a deeper symmetry like supersymmetry, a grand unified theory, or a staggering multiverse, the wild variation in particle masses stands as a silent testament to the fact that our current understanding is incomplete. The sheer, unjustified randomness of these numbers is a siren call, urging us to look beyond the standard model for a theory that can truly explain why the building blocks of our reality weigh what they do. And so we return to the cosmological constant, to that infamous number 10 to the negative 120, a value so small it feels less like a measurement and more like a profound message from the universe, a whisper in the void that something in our fundamental understanding is deeply, perhaps even radically, wrong. This isn't just a minor accounting error in the cosmic ledger. It represents the single greatest mismatch between theoretical prediction and observational fact in the entire history of science. To truly grasp the magnitude of this problem, we need to understand where that prediction comes from. According to our well-tested theory of quantum mechanics, the vacuum of space is not empty. It is a seething, bubbling foam of virtual particles, pairs of particles and antiparticles that spontaneously flicker into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This isn't just theoretical speculation. We see the effects of this quantum frenzy in laboratory experiments, like the Casimir effect, where two metal plates placed incredibly close together in a vacuum are gently pushed toward each other by the pressure of these virtual particles popping off outside them. Every cubic centimeter of empty space, according to quantum field theory, is teeming with this energy. When physicists attempt to calculate the total energy density of this quantum vacuum, they do so by summing up the contributions from every possible quantum field, all the way down to the highest energy scales, the Planck scale. The result they get is an energy density of about 1 in these natural units, but the value we actually observe from measuring the acceleration of the universe's expansion is not 1. It is 0.000000, and you would need to write out 119 more zeros after the decimal point before you finally got to a 1. The prediction is too large by a factor of 10 to the 120th power. This is a number so unimaginably vast that it exceeds the number of atoms in the entire observable universe. It is the equivalent of a theory predicting that a single drop of water should possess the energetic potential to vaporize all the world's oceans, while our actual measurement shows it can barely raise the temperature by a millionth of a degree. This is the cosmological constant problem in its full, terrifying glory. Why is the energy of the vacuum, the weight of nothingness itself, not the colossal, universe-shattering force it should be, but instead this faint, barely there whisper? For decades, physicists have searched for a mechanism, a missing piece of physics that would naturally cancel out this enormous vacuum energy, leaving behind the tiny residue we observe. One of the most promising ideas was supersymmetry. This elegant theory posits that for every known particle, there exists a super-partner particle with a different spin. The beautiful mathematical consequence of this symmetry is that the quantum contributions to the vacuum energy from ordinary particles would be exactly cancelled out by the contributions from their super-partners. The positive energy from one set would be perfectly balanced by the negative energy from the other, potentially driving the net cosmological constant to zero. It was a gorgeous, natural solution. There was just one catch. For the cancellation to be perfect, supersymmetry must be an unbroken symmetry of nature. But if that were true, we would have found these super-partner particles already. They would have the same mass as their ordinary counterparts. The fact that we have not found a selectron with the same mass as an electron means that supersymmetry, if it exists, must be a broken symmetry at the energy scales we can probe. And once it is broken, the cancellation is no longer perfect. It might reduce the discrepancy, but it still leaves a remainder that is billions upon billions of times larger than the value we observe. Supersymmetry might solve other hierarchy problems, but it falls devastatingly short of solving this one. Faced with the failure of such elegant mechanical solutions, some of the world's most renowned physicists have been driven to consider a far more radical and to some unsettling explanation. This is the landscape multiverse idea born from string theory. String theory, a leading candidate for a theory of quantum gravity, suggests that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. One of the consequences of this theory is the prediction of a vast number of possible stable configurations. For the extra dimensions, it requires perhaps 10 to the 500 or more. Each of these configurations corresponds to a universe with a different set of physical laws and, crucially, a different value for the cosmological constant. This unimaginably huge collection of possibilities is known as the string theory landscape. In this view, our universe is just one tiny bubble in a frothing multiverse, a single data point in a near-infinite ensemble. Most of these universes have a cosmological constant that is either enormously positive, causing them to inflate apart too rapidly for any stars or galaxies to form, or enormously negative, causing them to recollapse into a big crunch instantly. But through sheer, mind-numbing statistics, a vanishingly small fraction of these universes will, by pure chance, have a cosmological constant very close to zero. And it is only in those rare, habitable universes that life can ever arise to ponder the question. As physicist Leonard Susskind, a chief architect of this idea, articulated, the anthropic principle becomes a selection effect. We do not observe a large cosmological constant because we could not possibly exist in a universe that had one. The value isn't explained by a fundamental law. It is explained by our own existence as observers. It is a cosmic example of survivorship bias. This leads us to a profound and almost philosophical crossroads. Is the incredible smallness of lambda due to this kind of environmental selection in a multiverse, a grand cosmic accident that just happened to work in our favor? Or does it point to a fundamental symmetry or dynamical mechanism that we have not yet discovered, a principle that would force the vacuum energy to be zero or nearly zero, making our universe not a lucky accident but an inevitable outcome. The multiverse explanation can feel, to many, like a retreat from the traditional goal of fundamental physics, to find a unique, predictive theory of why the universe is the way it is. Yet, it also opens the door to a reality of breathtaking vastness and complexity. The cosmological constant problem, this puzzle of the smallest number, ultimately forces us to ask the biggest questions about the nature of existence, causality, and the very limits of scientific explanation. It stands as a humbling reminder that the universe is under no obligation to conform to our human sense of elegance and naturalness, and that the final answer may require us to expand our conception of reality far beyond the single, familiar universe we call home. Now, from the ghostly lightness of neutrinos and the stubborn lithium deficit, we turn to a prediction so bold it challenges the very permanence of the matter that makes us up. Grand unified theories, or GUT, represent one of the most ambitious dreams in physics, to describe the electromagnetic, weak, and strong nuclear forces as different manifestations of a single, primordial force that existed in the universe's first moments of unimaginable heat and energy. This is a quest to complete the unification that started with James Clerk Maxwell connecting electricity and magnetism, and continued with the electroweak theory. But this next step comes with a truly staggering and testable prediction that the proton, the very bedrock of atomic nuclei and by extension all visible matter in the cosmos, is not truly immortal. According to these grand theories, the proton should eventually decay, vanishing in a fleeting burst of energy. Its estimated lifetime, however, is not something we can easily witness. It is an almost metaphysical number, around 10 to the 34th years or even longer. To grasp the scale of that number, consider that the current age of our universe is only about 13.8 billion years, which is 10 to the 10th years. A proton's lifetime is a 10 followed by 34 zeros, a time span that dwarfs the current cosmic age by 24 orders of magnitude. It is a number that speaks not of fleeting instability, but of an almost perfect, profound stability that defines the reality we experience. The reason for this incredible longevity is directly tied to the immense energy scale at which this grand unification is thought to occur. In the framework of these theories, developed by pioneers like Howard Georgi and Sheldon Glashow, the three forces become one at energies around 10 to the 16th gigaelectronvolts. This is an energy realm a trillion times more powerful than what our most mighty particle collider, the Large Hadron Collider, can ever hope to achieve. It is an energy so far beyond our direct reach that it might as well be in another universe. And in the quantum world, processes that happen at such incredibly high energies must, by the uncertainty principle, correspond to incredibly rare events and incredibly long timescales in our low-energy world. The probability that a quark inside a proton will quantum tunnel through the immense energy barrier required to trigger its decay is almost infinitesimally small. The inverse of the proton's lifetime is a very, very small number, and that small number is a direct measure of the height of that energy barrier. So, by searching for the extremely rare event of a proton dying, we are indirectly probing physics at energies we can never hope to recreate in a laboratory, testing the very heart of these majestic unified theories. This search is not a mere theoretical exercise. It is one of the most epic and prolonged experiments in the history of science. The primary tool for this hunt is the Super Kamiok and detector in Japan, a colossal cavern filled with 50,000 tons of ultra-pure water, buried deep beneath a mountain to shield it from the constant rain of cosmic rays that would otherwise drown out the signal. Lining this vast tank are over 13,000 incredibly sensitive light detectors, waiting to see the telltale flash of Cherenkov radiation, that would be produced if a proton inside a water molecule were to decay. The experiment must be exquisitely sensitive because the predicted decay rate is so low. With 10 to the 34 protons in the detector, you might expect to see just a handful of decays per year. Researchers have spent decades watching, analyzing every flicker of light, every potential signal, and yet, so far, the proton has stubbornly refused to die on cue. Not a single, unambiguous event of proton decay has ever been witnessed. This null result is profoundly important. It has already ruled out the simplest and most elegant versions of grand unified theories, those that predicted a lifetime closer to 10 to the 30 years. The proton's enduring stability has forced theorists back to the drawing board to develop more complex and nuanced models, often incorporating ideas from supersymmetry, which can push the predicted lifetime to even more extreme values, perhaps 10 to the 35 years or longer. This incredible patience, this decades-long vigil in underground labs, highlights a beautiful and counterintuitive truth in fundamental physics. Sometimes, the most powerful test of a theory about the highest energies and the smallest scales is not found by making something happen, but by waiting for something that almost never does. The search for proton decay is a perfect example of how a vanishingly small number, the inverse of a probability so tiny it defies human intuition, can serve as a direct window into a grander, more unified reality. It connects the fate of a single subatomic particle in a Japanese mine to the fiery conditions of the universe's first trillionth of a second. Howard Georgi himself has reflected on this, noting that while the simplest GUTs may be challenged, the core dream of unification remains compelling, and the proton's continued existence simply guides us toward the right path. Every day that the proton survives, it whispers a clue about the specific structure of a theory that lies far beyond our current horizon, proving that in the quest for understanding, even nothingness can be the most valuable data of all. But if the stability of matter hinges on the incredible rarity of proton decay, then the story of entropy asks an even deeper question about the universe's most improbable beginning. Entropy, in its simplest terms, is a measure of disorder, of randomness. It's the reason ice melts in a warm room, why smoke disperses in the air, and why we remember the past but not the future. It defines the arrow of time itself, and when we calculate the total entropy of the entire observable universe, every star, every galaxy, every particle within our cosmic horizon, we arrive at a number that is, by any human standard, astronomically large, roughly 10 to the power of 101. This number, representing the number of ways all the constituents of the cosmos can be arranged, is so vast it defies comprehension. Yet, in the grand scheme of what is physically possible, this number is shockingly, inexplicably small. If the universe were a box full of gas particles, its maximum possible entropy would be almost unimaginably larger. Our universe, for all its swirling galaxies and cataclysmic supernova, is in a state of incredibly low entropy. It is a cosmic monument to order, not chaos. This profound and puzzling fact is not a feature of the present, but a relic of the most distant past. The universe was born with an unbelievably low entropy. The Big Bang was not a chaotic explosion in the way we typically imagine it. It was a state of exquisite, almost perfect uniformity. The primordial soup of particles was incredibly smooth and ordered, with only the tiniest quantum-scale ripples breaking the perfect symmetry. This is the ultimate paradox. The hot, dense fireball of the beginning was actually a state of very high order. As the universe has expanded and evolved over billions of years, it has been relentlessly climbing toward higher entropy, transforming that initial order into the complex structures we see today. Gravity is the master architect of this transformation. That initial smoothness was actually a state of very low gravitational entropy. As gravity pulled matter together, it created pockets of extreme density stars, galaxies, black holes, which, counterintuitively, represent a much higher state of overall disorder. A black hole, for instance, is the ultimate entropy sink. A single one can contain more entropy than all the stars and gas in a galaxy combined. So the universe's journey from a smooth beginning to a lumpy, structured present is actually a journey from low entropy to high entropy, driven by the relentless pull of gravity. The real mystery, the profound why, is not why the universe is becoming more disordered now, but why it started in such an incredibly ordered state in the first place. Out of all the possible initial conditions, why did it choose one of such spectacularly low probability? This question has led to some of the most speculative and breathtaking ideas in all of cosmology. The renowned physicist and mathematician Roger Penrose has spent decades grappling with the enigma of the low entropy beginning. His answer is as radical as it is beautiful: conformal cyclic cosmology. Penrose proposes that our universe is not a one-off event, but just one eon in an endless cycle. In this model, the far, far future of our universe, a cold, empty, and featureless void dominated by exponentially expanding dark energy, becomes mathematically indistinguishable from the ultra-smooth, low-entropy Big Bang of a new eon. In this transformation, all information about particles, masses, and even the dimension of time itself is lost or reset through a process called conformal scaling. The immense entropy of our dying universe is effectively erased, and the slate is wiped clean for a new beginning. The incredibly low entropy of our Big Bang is therefore not a mysterious starting point, but a natural consequence of the death of a previous universe. It's a cosmic phoenix rising from the ashes of maximum disorder into a new state of pristine order, ready to begin the long climb back toward chaos all over again. It's a grand, poetic vision that does away with the need for a singular beginning entirely, replacing it with an eternal, cyclic process. Penrose even suggests we might find evidence for this in the cosmic microwave background, the afterglow of our own Big Bang. He has pointed to strange, circular patterns in the CMB map that he interprets as the imprints of unimaginably violent collisions between supermassive black holes from the previous eon, their gravitational waves etched onto the very fabric of our newborn universe. While this evidence remains highly controversial and is not accepted by most cosmologists, it illustrates the profound lengths to which scientists are willing to go to solve this puzzle. The alternative to such a cyclic model is to accept that our universe began in a state of such astronomically low probability that it seems to demand an explanation beyond pure chance. This brings us back once again to the multiverse and anthropic reasoning. Perhaps in a vast multiverse, nearly all universes begin with high entropy and immediately devolve into formless nothingness. Only in an exceedingly rare few does a fluctuation create a Big Bang with low enough entropy to allow for a long and complex cosmic evolution. We, of course, find ourselves in one of those rare, ordered universes because it's the only kind that can support observers. The small number that represents our universe's improbability becomes a selection effect, a necessary ticket for admission into a universe that has a history and a future. Whether the answer lies in Penrose's cycles or a vast multiverse, the entropy of the universe forces us to confront the most fundamental questions about existence. Why is there an arrow of time? Why does the past look so different from the future? It all traces back to that one incredibly special, low entropy state some 13.8 billion years ago. The universe's capacity for beauty, for structure, for life itself, is a direct consequence of this initial order, a precious and improbable inheritance that we are still, to this day, spending down. And just as the initial low entropy of the universe presents a cosmic why, a modern and pressing mystery brings us back to the very fabric of cosmic evolution, one that hinges on a number that is anything but constant in our measurements. This is the Hubble constant tension, a disagreement that at first glance seems almost trivial, a discrepancy of just a few percentage points in the value of the universe's current expansion rate. But in the world of precision cosmology, where scientists measure the faintest echoes of the Big Bang to the tiniest flickers of distant stars, this small difference is a roaring siren, a potential crack in the foundation of our understanding that might just be the most important clue we have to new physics. The Hubble constant, denoted as h0, is one of the most fundamental numbers in all of cosmology. It tells us how fast the universe is expanding today, the current rate at which galaxies are rushing away from us. Measuring it should, in theory, be straightforward. You find a galaxy, measure its distance, measure how fast it's moving away from us due to the expansion of space, and then do the simple division. Velocity divided by distance equals h0. The challenge, of course, is in the simple part. Measuring astronomical distances with extreme accuracy is one of the hardest problems in all of science. Over the decades, astronomers have built a cosmic distance ladder, a series of interlocking methods where each rung calibrates the next. The first rung uses parallax, the tiny apparent shift of nearby stars as Earth orbits the Sun, to get solid distances. These are used to calibrate the next rung, which uses Cepheid variable stars whose pulsation periods are directly tied to their intrinsic brightness. By measuring how bright they appear compared to how bright we know they are, we can calculate their distance. Cepheids then calibrate the final rung, type Ia supernova. These are stellar explosions so uniform in their peak brightness that they are considered standard candles, visible across billions of light years. Using this meticulous ladder, teams led by astronomers like the renowned Wendy Friedman have spent years peering at galaxies with the Hubble Space Telescope, painstakingly building a local measurement of the expansion rate. Their latest results are incredibly precise, pointing to a value of around 73 kilometers per second per megaparsec. This means that for every megaparsec, about 3.3 million light-years, a galaxy is from us. It appears to be moving away 73 kilometers per second faster. But there is another, completely independent way to measure the Hubble constant, one that doesn't use the distance ladder at all. It comes from looking at the very oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang. Incredibly detailed maps of this faint radiation, most famously from the Planck satellite, show us the universe as it was just 380,000 years after it began. By applying our exquisitely tuned model of cosmic evolution, the lambda-cold dark matter model, to this baby picture of the cosmos, we can run the clock forward and predict what the Hubble constant should be today. This method is a powerful consistency check on our entire standard model of cosmology, and the prediction it gives is very clear and, crucially, in stark disagreement with the local measurements, about 67 kilometers per second per megaparsec. 67 versus 73, a difference of about 9%. This is the Hubble tension. 9% might not sound like much, but the uncertainty in each measurement is now down to just 1 or 2%. This means the gap between them is not a blurry overlap. It is a clear, stubborn, and statistically significant chasm. As Wendy Friedman has aptly noted, the community is now past the point of dismissing this as a simple error. The disagreement is real, and it is forcing us to ask an electrifying question. After over a century of cosmology, could it be that we are missing something fundamental about how the universe works? The possible resolutions to this tension fall into two broad and equally thrilling categories. The first is the more conservative but still profound possibility of hidden systematic errors. Perhaps there is an unseen flaw in how we build the cosmic distance ladder. Maybe Cepheid variables are not as perfectly standard as we believe, or perhaps there is some unknown dust or population effect in the host galaxies of supernova that is subtly skewing our measurements. Teams are working tirelessly to find and eliminate these potential errors, using new tools like the James Webb Space Telescope to observe Cepheids with unprecedented clarity in infrared light, cutting through the dust that can obscure their true brightness. If the error is on the Planck side, it could be that our model for interpreting the cosmic microwave background has a subtle flaw. But as these efforts continue to refine both methods and the discrepancy only grows more robust, the second category of explanation becomes increasingly compelling: new physics. This is where the tension transforms from a problem into a potential portal. If both measurements are correct, then our standard model of cosmology must be incomplete. The lambda-CDM model that worked so perfectly to predict the CMB might need an upgrade. What new ingredient could we be missing? The list of candidates is a tour of the most exciting frontiers in theoretical physics. Perhaps dark energy, the mysterious force accelerating the expansion, is not a constant after all. Maybe it evolves over time, growing stronger or weaker in a way that would change the expansion rate between the ancient universe and today. Or maybe dark matter has properties we haven't accounted for. It could interact with itself or with light in a subtle way that alters how structures form. Some theorists have even proposed more exotic ideas, like the existence of a new type of relativistic particle that flooded the early universe, or that our universe has a slight, large-scale curvature that we have failed to detect. Each of these ideas would require a rewrite of some chapter in our cosmic story. The Hubble constant tension is a perfect, modern embodiment of the central theme that the smallest numbers in physics often hold the biggest clues. A single, seemingly minor numerical disagreement is now driving a renaissance in cosmological thought, pushing our experiments to greater precision and our theories to greater creativity. It stands as a powerful reminder that science does not advance when all the numbers agree, but precisely when they don't. This tiny tension in a fundamental constant is a tug on the curtain, hinting that there is so much more to the universe's grand production than we have yet seen from our limited seats. But while the Hubble tension deals with the grand scale of the cosmos, another set of incredibly small numbers governs the interactions of the tiniest building blocks of matter, numbers that ultimately decided the fate of everything we see. Deep within the equations of the Standard Model lies a 3x3 grid of numbers known as the Kabibo-Kobayashi-Maskawa matrix, or CKM matrix for short. This isn't just any mathematical table. It is the rulebook that dictates how quarks, the fundamental particles that make up protons and neutrons, communicate with each other through the weak nuclear force. Think of the 6 types of quarks as being grouped into 3 families or generations. The up and down quarks are the first and most common generation, forming the protons and neutrons in every atom. The charm and strange quarks are a heavier second generation, and the top and bottom quarks are the immensely massive third. In a perfect, simple world, the weak force would only allow quarks to interact with their direct partners in the same generation. An up quark would only turn into a down quark, a charm quark only into a strange quark. But our universe is not that simple. The CKM matrix tells us that the lines between these families are blurry. Its off-diagonal elements, those numbers not on the main diagonal, are small but definitely not zero. This means that every so often, an up quark can decide to become a strange quark instead of a down quark, or a top quark can transform into a bottom quark. It's as if there's a tiny amount of leakage between the generations, a subtle crosstalk that allows quarks to occasionally jump families. The values in this matrix are some of the most precisely measured numbers in all of physics, and they are decidedly odd. The probability that a down quark will interact with a strange quark is governed by the sign of an angle called the Cabibbo angle, which is about 13 degrees. That's a small angle, and its sign is a small number around 0.22. But the angles that describe the mixing with the third generation are even smaller, almost vanishingly so. This hierarchy of small numbers means that cross-generational jumps are possible, but they are very, very rare compared to interactions within a family. This is why we don't see protons spontaneously transforming into particles made of strange quarks in everyday matter. The leakage is too faint, but it does happen. And this subtle imperfection in the laws of physics is one of the most important features of our universe. These small numbers in the CKM matrix are far more than a technical detail. They are the direct cause of a phenomenon known as CP violation. CP stands for charge and parity. It's a fundamental symmetry that, if perfectly obeyed, would mean that the laws of physics treat particles and their mirror image antiparticles exactly the same way. For a long time, physicists assumed this symmetry was perfect, but the small, complex phases in the CKM matrix break this symmetry. It means that there is a tiny, fundamental difference in how particles and antiparticles behave under the weak force. The consequences of this minuscule breaking of symmetry are literally cosmic in scale. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. If that were true, all those particles and antiparticles would have eventually met and annihilated each other in a flash of pure energy, leaving behind a universe containing nothing but light. The fact that you, the Earth, and the galaxies exist is proof that something must have tipped the scales. There must have been a process that created just a tiny bit more matter than antimatter. Roughly one extra particle of matter for every billion matter-antimatter pairs. That 1 in a billion surplus is all the stars, planets, and life in the universe. CP violation, sourced from those small numbers in the CKM matrix, is the leading candidate for creating that surplus. It provided the mechanism that could slightly favor the production of matter over antimatter in the universe's first moments, allowing a residue of matter to survive the Great Annihilation. The man who helped uncover this profound connection, Japanese physicist Makoto Kobayashi, shared the Nobel Prize in 2008 for this work. Along with his colleague Toshihide Masukawa, he extended the original two-generation quark mixing idea of Nicola Cabibbo to 3 generations. Kobayashi and Masukawa made a stunning prediction. If there were only 2 generations of quarks, CP violation could not occur. But if a third generation existed at a time when only 3 quarks were even known, then their mathematical framework would naturally allow for CP violation through a complex phase in the matrix. It was a breathtaking theoretical leap that implied the existence of entirely new particles, the bottom and top quarks, which were later discovered exactly as predicted. Kobayashi reflected that they were simply following the mathematics to its logical conclusion, unaware they were solving one of the universe's deepest mysteries. The small angles and phases they were working with weren't chosen. They were discovered by experiment to be just so. Yet for all its success, the CKM matrix doesn't tell us why these numbers have the values they do. Why is the Cabibbo angle 13 degrees and not 30? Why are the other mixing angles so much smaller? This is the lingering puzzle. The values seem arbitrary, another set of free parameters that must be plugged into the standard model. Many theorists believe these specific values are not random but could be clues to a deeper theory, one based on a higher symmetry or perhaps a new layer of reality. Some grand unified theories attempt to derive the CKM matrix values from first principles, suggesting they are the broken remnants of a perfect symmetry that existed at ultra-high energies. Others have proposed connections to the similarly mysterious masses of the quarks themselves. The smallness of the cross-generational mixing could be related to the vast hierarchy in mass between the quark generations. The heavier the quarks involved, the weaker the leakage between them seems to be. This hints at a deeper connection between mass and mixing that we do not yet fully understand. So this collection of small numbers, measured with incredible precision in particle accelerators around the world, ultimately writes the rulebook for our existence. They govern the rare transformations of quarks, they break a fundamental symmetry of nature, and they provide the mechanism that allowed a universe of pure energy to become a universe filled with something. The CKM matrix is a powerful demonstration that the most profound cosmic consequences can hinge on the tiniest of numerical values, a faint but indelible signature etched into the laws of physics that made all the difference. Now, let's shift our focus from the vast cosmic scales of the Hubble constant to the incredibly precise world of a single, unstable particle, the muon, and a tiny anomaly in its behavior that has sent ripples of excitement through the world of physics. This is the story of the G-2 Anomaly, a tale where a discrepancy in the 8th decimal place isn't a rounding error, but a potential crack in the foundation of the standard model, a tiny window into a hidden reality. The muon is often described as the electron's heavier, unstable cousin. It's a fundamental particle that behaves almost exactly like an electron, but it's about 200 times more massive and decays into other particles in a mere 2/millionths of a second. This extra mass makes the muon far more sensitive to the quantum vacuum, that seething foam of virtual particles we discussed earlier. This sensitivity is the key to our story. Just like electrons, muons have a tiny internal magnet, a property physicists call their magnetic moment. The strength of this internal magnet is represented by a value called the G-factor. For a simple, point-like electron, Dirac's theory predicted this G-factor should be exactly 2, but thanks to quantum mechanics, we know it's not that simple. The quantum vacuum constantly whispers to the muon, virtual particles, photons, electrons, even hypothetical new particles pop in and out of existence around it, subtly influencing its magnetic properties. This quantum correction is called the anomalous magnetic moment, and it's represented by the value G2 divided by 2. For the muon, this anomaly is a small but very precise number that our most advanced theories can calculate with astonishing accuracy. It is a number that should encapsulate the influence of every known particle and force in the standard model. The magic of this measurement is that it serves as an incredibly sensitive test of our entire theoretical framework. Theorists use supercomputers and complex equations to predict the exact value of the muon's G2, accounting for every known virtual particle's contribution. Meanwhile, experimentalists perform breathtakingly precise measurements to see if reality agrees. It's like predicting the exact weight of a grain of sand by calculating the gravitational pull of every mountain, ocean, and planet in the solar system, and then checking it on a scale sensitive enough to detect a few extra atoms. For decades, a previous experiment at Brookhaven National Laboratory in the United States had hinted that the measured value was slightly larger than the standard model prediction. The difference was tantalizing but sat right on the edge of the margin of error, leaving physicists in a state of suspense. Was it a fluke, or was it the first whisper of something new? This is where the story accelerates. To resolve the mystery, a new experiment was built at Fermilab, designed with one purpose: to measure the muon's magnetic moment with unprecedented precision. The experiment is a masterpiece of modern physics. It starts by creating a beam of muons and injecting them into a gigantic, superconducting magnetic storage ring, 14 meters across. These muons whiz around this ring at nearly the speed of light. In the presence of the powerful magnetic field, the direction of each muon's spin, think of it as the axis of its tiny internal magnet, precesses or wobbles like a slowing top. The rate of this wobble is directly proportional to the value of G2. The key to the experiment is monitoring the fate of these muons as they decay. When a muon decays, it always spits out an electron in the direction of its spin at that exact moment. By placing incredibly sensitive detectors around the ring and counting the electrons that hit them, scientists can map the wobble of the muon's spin with mind-boggling precision. They are not watching the muons themselves, they are reconstructing their dance by listening to the echoes of their deaths. The first results from Fermilab were announced in 2021, and they sent a shockwave through the scientific community. They confirmed the Brookhaven result with even greater certainty. The measured value of the muon's anomalous magnetic moment definitively disagrees with the standard model prediction. The difference is still a tiny number, but it is now a difference of 4.2 standard deviations. In the language of physics, this is a very strong hint that the discrepancy is real. It's not a statistical fluctuation. The probability that this is a random chance is about 1 in 40,000. This is not quite the golden standard of 5 sigma needed to claim a definitive discovery, but it is powerfully suggestive. It means that the quantum whispers the muon is hearing do not match the chorus of all the known particles. There is an extra, faint voice in the choir, one that belongs to a particle or force we have not yet discovered. So what could this new voice be? The tiny size of the anomaly is itself a clue. It suggests that whatever is causing this effect is only interacting with the muon very weakly, or it is a very heavy particle that is hard to produce virtually. This has led physicists to propose some of the most exciting ideas in modern particle physics. Could this be the long-awaited sign of supersymmetry? Many supersymmetric models predict the existence of superpartners, like neutrinos or smuons, that would contribute to the muon's magnetic moment in just this way. The Fermilab result has breathed new life into these theories, guiding them toward the specific parameter space where such particles might hide. Alternatively, could the muon be sensing the presence of a hidden sector of dark matter? Some theories propose new force-carrying particles that interact with ordinary matter only very feebly. A particle like a dark photon or a Z-prime boson could easily account for the measured anomaly. There are even more exotic possibilities, like the muon interacting with hypothetical particles that hint at extra dimensions. The pursuit of this small number is a beautiful example of how science operates at the frontier. It is a meticulous, decades-long conversation between theory and experiment, where each refines the other. The theorists are now scrambling to recalculate their standard model predictions with even greater care, ensuring that the discrepancy is not due to a miscalculation of the known contributions, particularly from the strong nuclear force. The experimentalists at Fermilab are continuing to take more data, aiming to slash their uncertainties in half and reach that definitive 5 sigma discovery threshold. This isn't just about one number, it's about using the muon as a hypersensitive probe, a natural quantum laboratory that can detect the faintest shadows of new physics lurking just beyond our current sight. The G2 anomaly demonstrates with stunning clarity that sometimes the most profound secrets of the universe are hidden not in the loud, dramatic collisions of particle accelerators, but in the silent, precise wobble of a lonely particle dancing in a magnetic field, counting its last moments. Yet even as we marvel at the muon's sensitive wobble, we must venture deeper into the quantum realm, to the very source of that whispering vacuum, to the fundamental jitter that underpins all of reality: quantum fluctuations. If the universe were a silent, static void, these fluctuations would be its background hum, an eternal fizz of spontaneous activity that occurs even in the complete and total absence of anything else. They are a direct and unavoidable consequence of the Heisenberg uncertainty principle, which tells us that on the smallest scales there is a fundamental trade-off. We can never know both the exact energy of a system and the exact time for which that energy exists. This allows for a fascinating loophole. For incredibly brief moments, energy can seemingly be borrowed from nowhere, used to create a pair of virtual particles, a particle and its antiparticle, which then almost immediately annihilate each other and return the energy to the vacuum. This isn't a theoretical fantasy. It's a measurable feature of our universe, governed by the tiny value of Planck's constant, which sets the scale for this quantum fidgeting. The most famous demonstration of this effect is the Casimir effect, a stunning experimental validation of the quantum vacuum's energy. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a complete vacuum, just a few millionths of a meter apart. Classically, with nothing between them, nothing should happen, but the quantum world tells a different story. In the empty space outside the plates, every possible wavelength of virtual particles can flicker into existence. However, in the narrow gap between the plates, only those virtual particles whose wavelengths fit perfectly between the plates can appear. This creates an imbalance in the radiation pressure. There are simply more virtual particles popping into existence on the outside of the plates than on the inside. The result: the two plates are gently but measurably pushed together by the relentless pressure of this quantum foam. It is a ghostly force generated by nothing but the seething energy of empty space itself, a direct tap on the shoulder from the quantum world. But the influence of these tiny fluctuations doesn't stop at laboratory curiosities. It scales up to literally cosmic proportions. In the theory of cosmic inflation, the same kind of quantum jitter that causes the Casimir effect was writ across the entire universe. During that fantastically rapid expansion, the microscopic quantum fluctuations in the inflattened field, the field driving the expansion, were not allowed to simply vanish back into the vacuum. Instead, they were stretched by inflation from a quantum scale to a cosmic scale, frozen into the very fabric of space-time as tiny differences in density. Imagine a perfectly smooth sheet of rubber being stretched to the size of a continent. Any microscopic imperfection on its surface would be amplified into a major hill or valley. In exactly the same way, the infinitesimal quantum ripples became the primordial density perturbations, the seeds of all future structure. The slightly denser regions, ever so slightly more packed with particles thanks to those random fluctuations, had a little extra gravitational pull. Over billions of years, they drew in more and more matter, eventually growing into the vast cosmic web of galaxies, galaxy clusters, and superclusters that we see today. Every star, every planet, every structure in the universe can trace its origin back to a random quantum flicker in the first moment of time, amplified by inflation into the architecture of the cosmos. The scale of this process is almost beyond comprehension. The initial fluctuations were minuscule, on the order of 1 part in 100,000. The temperature variations we see in the cosmic microwave background, the baby picture of the universe, reflect this same tiny amplitude. Yet, this faint fingerprint was enough to trigger the gravitational collapse that built the entire visible universe. This profound connection between the quantum and the cosmic was a key insight for pioneers like Stephen Hawking, who worked tirelessly to understand how quantum mechanics and gravity intertwine. Hawking realized that even black holes, the most massive objects in the universe, are not immune to these quantum effects. His famous Hawking radiation shows that at the very event horizon of a black hole, quantum fluctuations can lead to particle-antiparticle pairs being created. If one particle falls in, the other can escape, making it appear as if the black hole is slowly evaporating. This stunning idea links the fate of the largest gravitational beasts to the smallest quantum tremors. This is the ultimate power of quantum fluctuations. They demonstrate that there is no such thing as true nothingness. The vacuum is alive with potential, a cauldron of spontaneous creation and destruction that is the engine of reality itself. From the ghostly force pushing two metal plates together to the majestic swirl of a galaxy, the influence of the smallest scales is imprinted on the largest. It is a breathtaking unification of concepts, revealing that the universe's grandest structures are, at their heart, quantum mechanical in origin. The cosmos did not begin with a smooth, featureless perfection, but with a faint, quantum-grained texture, a necessary imperfection that became the blueprint for everything that followed. But if the quantum fluctuations that seeded our universe were born from a process of unimaginable expansion, what was the engine that drove that incredible growth? The answer lies in the concept of a scalar field, a kind of cosmic fuel that filled the early universe and, for a brief moment, possessed a property so strange and counterintuitive that it could push space itself apart faster than the speed of light. This is the heart of inflationary theory, and it hinges on a set of conditions so precise, so delicately balanced, that they make the fine-tuning of the fundamental constants seem almost coarse by comparison. The field responsible for this expansion, often called the inflaton field, couldn't just be any field with any amount of energy. To power the smooth, exponential expansion that solves the horizon and flatness problems, its energy landscape, what physicists call its potential, had to be incredibly, almost unnaturally flat. Imagine this potential not as a steep mountainside, but as an vast, almost perfectly level plateau stretching off into the distance. Now picture a ball resting on this plateau. For inflation to work, this ball representing the value of the inflaton field must roll down this hill not with an accelerating rush, but with an excruciatingly slow and steady creep. This is the slow roll condition, and it requires that the hill be almost imperceptibly shallow. The steepness of the hill is described by small parameters in the equations, numbers that must be much, much less than 1. If the hill were even slightly steeper, the ball would pick up speed too quickly, ending the period of inflationary expansion almost before it began. The universe would not have enough time to stretch out and become smooth and flat. On the other hand, if the hill were completely flat, the ball wouldn't move at all, and the inflationary energy would remain trapped, acting like a permanent cosmological constant and never converting into the hot plasma of the Big Bang. The initial conditions require a breathtakingly precise balance, a sweet spot of incredible flatness that allows for a long, sustained period of gentle acceleration. This is the fine-tuning puzzle of inflation in a nutshell. Why did the universe choose a scalar field with a potential that was so perfectly suited for the job? It seems like yet another incredible coincidence, another set of dials that just happened to be set exactly right. This fine-tuning was not lost on the creators of the theory. Alan Guth, who first proposed the revolutionary idea of inflation in 1980, openly acknowledged this issue. He famously noted that while inflation resolves many of the great problems of the standard Big Bang model, it does so at a cost. It requires these very specific initial conditions. The theory doesn't explain why the universe began in that particular state. it simply assumes it. Andre Linde, who developed the subsequent chaotic inflation model, offered a different perspective. He suggested that perhaps the initial value of the inflatoned field could have been random, a product of quantum fluctuations in a pre-existing spacetime. In this view, while most regions of this primordial universe would not have had the right conditions for inflation, some patches, just by sheer chance, would have had a sufficiently flat potential and a high enough starting value to trigger a runaway expansion. In those lucky patches, inflation would take hold, blowing them up to enormous sizes, each becoming a separate, self-contained universe. Our entire observable cosmos would then be just one such inflated patch within a much larger, perhaps infinite, meta-universe. This idea naturally leads to the concept of eternal inflation and a multiverse. Once begun, inflation might be impossible to stop everywhere at once. Quantum fluctuations could continuously create new regions where the inflatoned field remains high, triggering new bouts of inflationary expansion in an endless fractal-like cascade. In this eternal inflation scenario, our universe is not unique. It is one bubble in a vast cosmic foam, a single outcome in a landscape of possibilities. The fine-tuning of the inflatoned potential is then not a mystery to be solved by a unique law, but a selection effect. We find ourselves in a bubble where inflation lasted just long enough to produce a large, flat, and smooth universe capable of hosting galaxies and life, not because such conditions are common, but because they are the only conditions under which we could possibly arise to ask the question. This multiverse interpretation transforms the small numbers governing inflation from a puzzle into a potential clue. The specific flatness of the potential in our patch might be a random outcome, but it could also be a signature of a deeper theory. Some proposals, particularly within string theory, suggest that the inflatoned field is not a fundamental entity, but a manifestation of the geometry of extra dimensions. The flatness of its potential could then be protected by a fundamental symmetry of the higher dimensional theory, making it a natural and expected outcome rather than a bizarre accident. Whether the answer lies in a multiverse or a deeper symmetry, the hierarchy of scalar fields in inflation powerfully reinforces the central theme that the smallest numbers in physics are rarely insignificant. They are the delicate fingerprints of the universe's origins, pointing beyond our local reality to a broader cosmological landscape whose true nature and extent we are only beginning to imagine. But within the elegant equations of quantum chromodynamics, the theory that describes the strong nuclear force gluing quarks together inside protons and neutrons, there lurks a ghost, a term that by all rights should be there, a parameter that the mathematics fully allows, but that nature itself seems to have gone out of its way to erase. This is the theta parameter, and its story is one of the most profound puzzles in modern physics, a mystery born from a number so small it borders on the absurd. Theta represents the potential for a specific kind of symmetry violation in the strong force, known as CP violation, just as the weak force exhibits this behavior through the Sinclair matrix, allowing for the matter-antimatter asymmetry that built our universe. The strong force's equations have a similar doorway. Theta is the knob that controls it. If this parameter had any significant value, it would imply that the laws of physics treat certain processes involving the strong force differently when viewed in a mirror and with particles swapped for antiparticles. The consequences would be dramatic and crucially observable. It would cause the neutron, which is electrically neutral, to develop a tiny electric dipole moment, a slight spatial separation between its positive and negative charges, making it behave like a microscopic bar magnet with a north and south pole. This isn't just a technicality, it would fundamentally alter the nature of neutrons and, by extension, all atomic nuclei. This is where the mystery deepens into sheer bewilderment. Physicists have designed incredibly sensitive experiments to measure the neutron's electric dipole moment, using ultra-cold neutrons and powerful magnetic fields to look for any telltale sign of this effect. The results are unequivocal. They have found nothing. The neutron is exquisitely symmetric. The experimental upper limit on the theta parameter is less than 1 part in 10 billion. It is not just small, it is zero for all practical purposes, a value so tiny it seems to scream that it is being hidden by something. This is the strong CP problem. Why is this parameter, which the mathematics so freely permits, so viciously suppressed in reality? It is a problem of naturalness. In the world of quantum field theory, parameters like theta typically receive huge quantum corrections from other particles and forces, which should drive its value up to something much larger, around 1. The fact that we observe it to be a billion times smaller than its natural value is a glaring anomaly, a sign that our understanding of the fundamental symmetries of nature is incomplete. It's as if a law of physics has been passed but is never, ever enforced, and we are left to wonder why. The most elegant and compelling solution to this conundrum was proposed in the late 1970s by Roberto Pexi and Helen Quinn, and its stunning implications were worked out by Frank Wilczek and Steven Weinberg. They realized that the theta parameter could be made to naturally vanish if a new, fundamental symmetry were added to the laws of physics. This symmetry would effectively allow the universe to dynamically adjust theta down to 0, solving the strong CP problem not by fiat, but by principle. But like all beautiful symmetries in quantum mechanics, this one would not be perfect. It would be spontaneously broken. And when a symmetry breaks, it gives rise to a new particle. Wilczek, with a playful nod to a household detergent, named this hypothetical particle the action because it was predicted to clean up a problem in the strong interactions. The action would be an incredibly light, electrically neutral particle that interacts only very weakly with ordinary matter, making it notoriously difficult to detect. But its properties are not arbitrary. They are precisely predicted by the theory invented to solve this very puzzle. This is where a solution to one deep mystery blossoms into a potential answer for another. The action, born from the need to explain a vanishingly small number in particle physics, turns out to be a prime candidate for the identity of dark matter. The same properties that make it so hard to find, its incredible lightness and feeble interactions, are exactly what many cosmological models require for a cold, dark matter particle that can clump together to form the gravitational scaffolding for galaxies without washing out the small-scale structures we observe. In the early universe, a vast number of these actions would have been created as the Pexi-Quinn symmetry broke, and they would have been born with very low energy, naturally settling into the dark matter halos that we now infer from the motions of stars and galaxies. The quest to detect the action is therefore a 2-for-1 hunt. Finding it would simultaneously resolve the strong CP problem and identify one of the most fundamental components of the cosmos. Experiments are underway using powerful magnetic fields and microwave cavities to try and convert these ghostly particles into detectable photons, a delicate process that requires technology at the very edge of our capabilities. Frank Wilczek often reflected on the beauty of this idea, how a theoretical problem of profound subtlety could point the way to a particle that might make up the majority of the universe's mass. It demonstrates a powerful truth in fundamental physics. The universe's most glaring omissions can be just as informative as its loudest presences. The inexplicable smallness of theta is not a detail to be brushed aside. It is a clue of the highest order. Does its near-zero value point to the existence of the action, a particle waiting in the shadows to be discovered? Or could it be evidence for an even deeper symmetry we have yet to conceive, a principle so powerful that it forbids CP violation in the strong interaction entirely? The strong CP problem stands as a monument to the fact that sometimes the most important thing a number can tell us is that it is missing. Throughout history, the human mind has been wired to seek patterns, to find meaning in apparent coincidences, and this drive has profoundly shaped our quest to understand the universe's fundamental numbers. One of the most captivating examples of this emerged in the 1930s, when the brilliant and unconventional physicist Paul Dirac noticed something astonishing. He observed that two vastly different calculations produced numbers of a similar, mind-bogglingly large scale. The first was the ratio of the strength of the electromagnetic force to the strength of gravity between two protons. This number is about 10 to the power of 36. The second was the age of the universe expressed in terms of the time it takes for light to cross an atomic nucleus, which also gives a number around 10 to the 36. Furthermore, the total number of protons in the observable universe is roughly 10 to the 78, which is 10 to the 36 squared. To Dirac, this couldn't possibly be a random accident. It felt like a profound clue. He proposed what became known as the large numbers hypothesis, suggesting that these enormous and seemingly related numbers were connected by a deep, underlying law of nature. His radical conclusion was that if these large numbers are related, then they must change together as the universe ages. This meant that what we consider constants, like the strength of gravity, might not be constant at all. In Dirac's evolving universe, the gravitational constant G would slowly decrease over billions of years. This idea sent ripples through the world of cosmology and physics. If gravity were weakening over time, it would have dramatic consequences for the history of our planet, the evolution of stars, and the very age we calculate for the cosmos. It was a breathtakingly elegant and simple solution to a numerical puzzle, and it inspired decades of experimental work to test the constancy of nature's laws. Researchers began meticulously measuring the light from incredibly distant quasars, looking for any subtle shift in the fine structure constant over cosmic time. They examined the precise isotopic ratios in the Oklo natural nuclear reactor, a 2-billion-year-old uranium deposit in Gabon, Africa, where the conditions of a spontaneous nuclear chain reaction are frozen in time. The physics of that reaction depends critically on the value of constants like alpha. If those constants were different 2 billion years ago, the reactor would have operated differently, leaving a fingerprint in the remaining nuclear waste. The results from Oklo and from the quasar observations have, so far, found no evidence for varying constants. The prevailing consensus is that the constants are indeed constant, and Dirac's numerical coincidence, while intellectually thrilling, was likely just that, a coincidence. This story is a powerful lesson in the scientific process, a cautionary tale about the seductive nature of numerology. The universe is full of numbers, and by pure chance, some of them will inevitably appear to line up in intriguing ways without any deeper meaning. For every fundamental constant, there are dozens of ways to combine them to create dimensionless numbers, and our pattern-seeking brains are exceptionally good at picking out the ones that seem special while ignoring the vast majority that do not. Most of these numerical coincidences are now seen as artifacts, mirages in the desert of mathematics that fade under the harsh light of stricter experimental scrutiny. They are reminders that correlation does not imply causation, even when the numbers are astronomically large. And yet, the story doesn't end there. The spirit of Dirac's quest, the insistence that these numbers must mean something, continues to inspire physicists today. While his specific hypothesis may not have panned out, the drive to explain why the constants have their specific values is stronger than ever. The fine-tuning problem we discussed earlier is, in a way, the ultimate numerical coincidence. The constants appear to be coincidentally perfect for life. This modern understanding has shifted the focus from looking for simple mathematical relationships between constants to asking a deeper, more profound question. Do these numbers point to a deeper structure, like a theory of everything, or do they point to a wider reality, like a multiverse? In this light, Dirac's intuition was perhaps not entirely wrong. He was just looking at the wrong set of numbers. The real coincidences aren't between the age of the universe and the force strength, but between the force strengths and the existence of complex structures. His fascination with large numbers opened a door, teaching us to be bold in our speculations but rigorous in our testing, a discipline that continues to guide the search for a larger reality hidden within the universe's most fundamental settings. But if the quest to understand the smallest numbers leads us to the edge of known physics, it finds one of its most astonishing expressions in the most extreme objects in the cosmos, black holes. For centuries, these gravitational monsters were thought to be the ultimate simplifiers, cosmic vacuum cleaners that swallowed everything that crossed their event horizon, leaving behind only three simple properties: mass, electric charge, and spin. They were the end of information, the ultimate paradox of a universe that otherwise seems to conserve it. Then, in the 1970s, a young physicist named Jacob Bekenstein made a stunning and deeply controversial proposal. What if a black hole wasn't a featureless pit, but actually possessed entropy? Entropy is a measure of disorder, of hidden information, and Bekenstein argued that a black hole's entropy must be proportional to the area of its event horizon. This was a radical leap. It suggested that the amount of information a black hole could contain was not related to its volume, like everything else in our experience, but to its surface area. The formula he derived is deceptively simple, yet it contains one of the most profound small numbers in all of physics. The entropy is equal to the area of the event horizon divided by 4, and then multiplied by a crucial constant. That constant is the Planck area. To grasp the significance of this, we need to step into the world of natural units. The Planck area is the square of the Planck length, which is about 10 to the negative 35 meters. This is an area so inconceivably small that it defies any human analogy. It is the fundamental pixel of space, the smallest possible unit of area that can have any physical meaning. Now consider a stellar mass black hole, an object with an event horizon that might be several kilometers across. Its surface area is enormous. When you divide that vast area by the minuscule Planck area, you get an astronomically large number, and that number is the black hole's entropy. This is a number so huge that it makes the entropy of all the stars, gas, and dust that collapse to form the black hole look utterly insignificant by comparison. A black hole is the most efficient repository of disorder in the entire universe, but within that immense result lies our small number, the 1/4. Why 1/4? Why is the entropy not just the area divided by the Planck area, but that value divided by 4? This specific, small numerical factor was not arbitrary. It fell out directly from the mathematics of general relativity and quantum mechanics when Stephen Hawking later discovered that black holes aren't completely black. They must radiate a faint glow of particles, now known as Hawking radiation, and they have a temperature. Hawking's calculation confirmed Bekenstein's insight and precisely fixed that factor of 1/4. This tiny fraction is a signature of quantum gravity, a direct link between the physics of the very large and the very small, written into the formula for the most enigmatic objects in existence. This discovery gave birth to the field of black hole thermodynamics, a set of laws that perfectly mirror the classical laws of thermodynamics but apply to these gravitational beasts. The implications of this are world-shattering. The fact that entropy is proportional to area, not volume, suggests a powerful and strange principle about the nature of reality itself. It led physicists like Gerard T. Hooft and Leonard Susskind to propose the holographic principle. Imagine a hologram, a two-dimensional surface that encodes all the information necessary to project a three-dimensional image. The holographic principle suggests that our entire three-dimensional universe, with all its stars, planets, and people, might itself be a projection from a two-dimensional surface at the very boundary of the cosmos. All the information that describes everything within a volume of space could be encoded on its outer surface. In this breathtaking view, the three-dimensional world we experience is a kind of illusion, a holographic movie playing out on a distant screen. The pixel size for this cosmic movie is the Planck area. The universe has a maximum resolution, and that resolution is set by this incredibly small number derived from the fundamental constants. This isn't just philosophy, it's a concrete research program in quantum gravity. The most successful implementation of this idea is the AD/S/CFT correspondence, a precise mathematical duality that shows a theory of gravity in a hypothetical higher dimensional volume is completely equivalent to a quantum field theory without gravity living on its lower dimensional boundary. The work of Bekenstein and Hawking fundamentally connected the world of the infinitesimal to the world of the colossal. Hawking's calculations showed that the temperature of a black hole is inversely proportional to its mass. A solar mass black hole has a temperature of a minuscule fraction of a degree above absolute zero, which is why we don't observe their radiation. But a tiny black hole, if one could exist, would be incredibly hot, radiating away its energy in a final flash. This temperature also involves the Planck mass and the speed of light, weaving the fundamental constants into the life cycle of a black hole. These discoveries suggest that space-time itself may not be smooth and continuous, as Einstein described it, but fundamentally pixelated at the Planck scale. The universe might be more like a digital image. If you could zoom in enough, you would eventually see the individual pixels. The incredible smallness of the Planck area is the reason we don't perceive this graininess in everyday life, just as we don't see the individual pixels on a high-resolution screen from a normal viewing distance. The entropy formula, with its reliance on the Planck area, is a powerful clue that we are living in a universe with a finite information capacity, a cosmic computer that operates with a fundamental limit on its smallest possible bit. The small numbers in black hole thermodynamics are not just curiosities, they are whispers from the deepest level of reality, telling us that the seamless, continuous world we perceive is built upon a hidden, discrete lattice, and that the key to unlocking the quantum nature of gravity is written in the geometry of nothingness itself. Yet for all its profound influence on the grandest scales, shaping the very architecture of galaxies and the fate of the cosmos, dark matter remains a ghost in the machine, a presence defined almost entirely by its absence. We feel its gravitational pull in the way stars whip around the centers of galaxies far too quickly, and in the way light bends around massive galaxy clusters, but the substance itself is utterly invisible to us. It neither emits nor absorbs light, and it seems to pass through ordinary matter as if it weren't even there. This incredible weakness, this near-total lack of interaction, is one of the most baffling small numbers in all of modern physics. To understand just how feeble this interaction is, we need to look at a parameter particle physicists call the cross-section. Imagine trying to shoot two tiny particles at each other. The cross-section is a measure of how big a target each one presents for a specific kind of interaction. For the strong nuclear force which holds atomic nuclei together, the cross-section is enormous on a quantum scale. For the electromagnetic force which makes your hands unable to pass through a table, it's still very significant. But for dark matter interacting with normal matter, the cross-section is almost vanishingly small. It is billions upon billions of times smaller than the cross-section for a typical nuclear reaction. This is why trillions of dark matter particles are streaming through your body every second without a single collision, without a single whisper of their passage. This profound isolation is the central mystery of dark matter. We know it must exist because of its overwhelming gravitational influence, a story famously pieced together by the meticulous work of astronomer Vera Rubin in the 1970s. By measuring the rotation speeds of stars in distant galaxies, she found something that defied explanation by the laws of gravity and the visible matter alone. Stars far from the luminous center of a galaxy were orbiting just as fast as those near the center, a behavior that would only be possible if each galaxy was embedded within a massive, invisible halo of matter, a halo that provides the extra gravitational glue to keep the stars from flying off into intergalactic space. As Rubin herself noted, the data presented a stark choice. Either our understanding of gravity was fundamentally wrong on a galactic scale, or there was about 6 times more matter in the universe than we could see. The scientific community largely converged on the latter explanation, but it came with a stunning implication. This dark matter not only doesn't glow, it barely talks to us at all. It is the universe's ultimate introvert, feeling the pull of gravity but shunning almost every other form of social interaction. So what could this elusive substance be? The quest to answer that question has given rise to a zoo of theoretical particles, each with its own proposed reason for being so shy. For decades, the leading candidate has been a class of particles known as WIMP, or weakly interacting massive particles. The weakly in their name is a bit of a pun. It suggests they interact primarily through the weak nuclear force, the same force responsible for certain kinds of radioactive decay. While the weak force is far stronger than gravity, it still has a very short range and a small cross-section, which would naturally explain why dark matter is so hard to detect. The elegance of the WIMP hypothesis lies in what physicists call the WIMP miracle. Calculations show that if a stable, massive particle with a cross-section typical of the weak force were left over from the Big Bang, it would naturally freeze out in just the right abundance to account for the dark matter we observe today. It was a beautiful, compelling idea that launched a global race to detect these particles directly. Experiments like LUX, Xenon, and Panda X have built incredibly sensitive detectors deep underground, shielded from cosmic rays, waiting for the once-in-a-lifetime event where a WIMP bumps into an atomic nucleus and creates a tiny flash of light or a minute amount of heat. But after decades of searching with ever more sensitive equipment, the results have been stubbornly silent. Not a single confirmed WIMP signal has been found, pushing the allowed cross-sections down to even smaller, more extreme values. This persistent silence has forced physicists to broaden their search to other, even more elusive candidates. This is where the action re-enters the story. As we discussed, the action was invented to solve a different problem, the strong CP problem in particle physics. But it just so happens to possess all the right qualities to be a compelling dark matter candidate. Actions would be incredibly light, possibly 1 trillion times lighter than an electron, and they would interact so feebly with ordinary matter that they make WIMP look like social butterflies. Their cross-section would be astronomically small. Instead of detecting them through rare nuclear collisions, experiments are trying to sense their presence by using powerful magnetic fields to convert them into extremely faint microwave photons. The fact that the action solves two profound puzzles at once makes it an extraordinarily attractive idea, a testament to how the universe might use a single, elegant solution to address multiple mysteries. Beyond WIMP and actions, the possibilities become even more exotic. Some theories propose that dark matter resides in a completely separate, hidden sector, a shadow universe of particles that have their own forces and interactions, but which only connect to our familiar world through the faintest of links, perhaps a yet undiscovered heavy particle that acts as a messenger. In this view, the smallness of dark matter's interaction isn't a fundamental property of the particle itself, but a consequence of this intermediary being very massive, suppressing the interaction. Others have wondered if dark matter interacts with itself more strongly than it does with us, through a dark force that we cannot feel. This could explain not only why we don't see it, but also how it clumps together to form the intricate cosmic web that scaffolds the visible universe. The incredible weakness of dark matter is a powerful reminder that the most dominant component of the material universe is, from our perspective, defined by a near zero. Its parameters are not just small, they are pushed to the very limits of detectability. This forces us to ask a humbling question: are we struggling to find dark matter not because our experiments aren't good enough, but because we are fundamentally deaf to the channel through it primarily communicates? Is its ghostly nature a clue that we are only perceiving a tiny slice of a much richer and more complex reality, one filled with forces and particles that operate entirely independently of the light and matter that make up our everyday world? The search for dark matter is ultimately a search for connection, an attempt to hear a whisper in a universe that seems to be shouting its presence through gravity alone, while maintaining an otherwise perfect and mysterious silence. But if the ghostly nature of dark matter challenges our perception of the cosmos, then the very first page of the universe's story presents a puzzle so profound it calls into question the entire notion of a random beginning. When we look out at the night sky, we see a universe rich with structured galaxies, clusters, and vast cosmic webs. But when we look back in time to the earliest light we can see, we find something shockingly different. The cosmic microwave background, that faint afterglow of the Big Bang, shows us a baby universe that is almost perfectly smooth. The temperature is the same everywhere to within 1 part in 100,000. This incredible uniformity, known as homogeneity and isotropy, is the deepest mystery of our cosmic origins. It's as if you took a handful of sand and threw it into the wind, and instead of scattering randomly, every grain landed to form a perfectly smooth, flawless sheet of glass stretching to the horizon. This is not what you would expect from a violent, chaotic explosion. It is a state of breathtakingly improbable order. This smoothness is the first and most crucial fine-tuned initial condition. For the universe to have evolved into the structured cosmos we see today, it had to start with these tiny, minuscule seeds of imperfection. Those 1 part in 100,000 fluctuations in density were the gravitational anchors that, over billions of years, pulled in more and more matter, eventually growing into the first stars and galaxies. Without them, the universe would have remained a forever featureless, expanding mist of hydrogen and helium, a sterile and lifeless void. But here's the catch. In the standard Big Bang model, without a mechanism like inflation, there is no reason for the universe to have been so smooth, or to have had just the right amplitude of fluctuations. The initial conditions had to be set with a precision that defies belief. The initial curvature of the universe had to be fine-tuned to within 1 part in 10 to the power of 15 to explain the flatness we observe today. That's a level of precision equivalent to balancing a pencil on its tip on the surface of the Earth, and coming back a billion years later to find it still perfectly balanced. It strains credulity to think this was simply a lucky accident. This is where the renowned physicist and mathematician Roger Penrose brings a devastatingly powerful argument to the table, one rooted in the second law of thermodynamics. As we discussed, entropy is a measure of disorder, and the universe is constantly moving from order to disorder. Penrose calculated the entropy of the early universe, that incredibly smooth, hot, dense state. He then compared it to the maximum possible entropy the universe could have had at that time, the entropy it would have had if it were in a state of total chaos and random motion. The result was staggering. The probability of the universe starting in such a low entropy, highly ordered state was about 1 chance in 10 to the power of 10 to the 123. This is a number so astronomically, mind-crushingly large that writing out the zeros would require more space than exists in the entire observable universe. It is perhaps the most improbable event imaginable. Penrose used this to argue that the initial conditions were not just fine-tuned, they were impossibly fine-tuned. The universe began in a state of such spectacularly specific order that it points to a fundamental gap in our understanding of its origins. For Penrose, the answer isn't a single, one-off beginning, but rather a cyclic cosmology where the end of a previous universe naturally gives rise to the low entropy start of the next. This incredible fine-tuning of the initial conditions is the ultimate foundation upon which everything else rests. The specific values of the fundamental constants govern the laws of physics, but the initial conditions set the stage upon which those laws can build a complex and interesting cosmos. The universe's capacity for beauty, for structure, for life itself, is a direct inheritance from that first, unimaginably special moment. It is a profound reminder that our existence hinges not just on the laws of nature, but on the very specific and seemingly miraculous way that nature chose to begin. Whether the answer lies in a cyclic universe, a multiverse, or a deeper physical principle we have yet to discover, the pristine smoothness of our cosmic dawn remains one of the most compelling clues that the smallest numbers, set at the very beginning, are the most important ones of all. But what if the universe's fundamental constants aren't dials that were set by hand, but are more like the climate of a specific region on a vast and varied planet? This is the breathtaking vision offered by string theory, perhaps the most ambitious attempt to unify all the forces and particles of nature under a single mathematical umbrella. At its heart, string theory proposes that the fundamental constituents of reality are not point-like particles but unimaginably tiny, vibrating loops of energy. And just as different vibration patterns on a guitar string produce different musical notes, the different ways these strings vibrate manifest as all the diverse particles we see: electrons, quarks, photons, and the rest. This elegant idea naturally incorporates gravity, promising a true theory of everything, but there's a catch, and it's a monumental one. For the mathematics of string theory to work consistently, it requires something our everyday experience never prepared us for: extra dimensions of space. Not just one or two, but 6 or 7 of them, curled up into a shape so small that we could never hope to perceive them directly. The properties of our universe, the values of those fundamental constants we've been puzzling over, are determined by the specific geometry of these hidden dimensions. Think of it like this: imagine a garden hose stretching off into the distance. From a distance, it looks like a simple one-dimensional line. But if you get up close, you discover it actually has a second dimension, a circular cross-section curled into a tiny loop. The size of that circular dimension matters. If you were a tiny ant living on the hose, your ability to move would depend critically on whether that circular dimension was large or small. In string theory, the 6 extra dimensions are curled up into an intricate, multi-dimensional shape known as a Calabi-Yau manifold. These shapes are not smooth spheres. They are complex, topologically rich objects with holes and handles, much like a multi-dimensional muffin or a complex coral. The precise shape of this Calabi-Yau space dictates everything. It determines the number of generations of particles, the masses of those particles, the strength of the forces between them, and even the value of the cosmological constant. The parameters we call constants are, in this view, not fundamental at all. They are the dynamic outcome of the geometry of hidden space. This is where the concept of moduli fields enters the picture. These are theoretical scalar fields that represent the possible ways the extra dimensions can be configured: their size, their shape, the angles between their various loops and handles. Each unique configuration of these moduli fields corresponds to a different vacuum state, a different possible universe with its own unique set of physical laws and constants. The unsettling revelation, as physicists like Brian Greene and Joseph Polchinski have extensively detailed, is that string theory doesn't predict a single, unique configuration. Instead, it allows for a stupendous number of stable possibilities. Current estimates suggest there could be 10 to the 500 or more distinct vacuum states. This is a number so vast that it exceeds the number of atoms in the observable universe by an almost unimaginable margin. This is the string theory landscape, a vast, perhaps infinite, collection of possible universes, a multiverse in the most literal sense. In this landscape, the question, why are the constants so small and finely tuned for life, undergoes a dramatic shift. It is no longer a question of fundamental law, but one of geography and selection. With 10 to the 500 possibilities, every conceivable combination of constants will be realized somewhere. The overwhelming majority of these universes will be stillborn cosmic deserts where the cosmological constant is too large and rips space-time apart instantly, or where the nuclear forces are too weak to ever form atoms, or where the electromagnetic force is too strong for chemistry to function. But by the sheer, crushing weight of probability, a minuscule fraction of these universes will, by pure chance, have the right combination of numbers to allow for the emergence of stars, planets, and conscious life. We quite necessarily find ourselves in one of those rare, bio-friendly universes. Our existence as observers acts as a selective filter. This application of the anthropic principle doesn't explain why the constants have their values in an absolute sense, but it does explain why we observe the values that we do. The small numbers are not designed, they are selected. As Polchinski put it, the landscape might be the only way to explain the small value of the cosmological constant without invoking a miraculous cancellation. It transforms a profound mystery of physics into a problem of statistics and environmental selection. This idea is as revolutionary as it is controversial. For some, it feels like a retreat from the traditional goal of physics, to find a unique, elegant, and predictive theory that explains why the universe must be the way it is. It exchanges that dream for a vast cosmic lottery where our universe is just a lucky ticket. For others, like Brian Greene, it is a thrilling expansion of reality's horizons, a paradigm shift that forces us to reconsider our place in the cosmos. We are not in a universe fine-tuned for life. We are life that has emerged in one of the rare universes capable of supporting it. The small numbers that seem so miraculous are, in this grander view, simply the local bylaws of our particular cosmic neighborhood, a tiny bubble in a frothing multiversal ocean. String theory's landscape offers a potential resolution to the fine-tuning enigma, not by eliminating the mystery, but by embedding it within a vastly larger and more complex reality. where the clues to our existence are written not in fundamental equations, but in the intricate, hidden geometry of dimensions we may never see. Capturing the faintest whispers of the universe requires instruments of almost unimaginable sensitivity, pushing the very limits of human engineering and patience. The quest to measure the smallest numbers in physics is not a task for the faint of heart. It is a battle against noise, against chance, and against the stubborn silence of nature itself. These experiments are monumental exercises in exclusion, where scientists must first imagine every possible source of interference, from the rumble of a distant truck to the subtle decay of materials in their own detectors, and then systematically build fortresses to keep those influences out. The goal is to create a perfect silence, a void of disturbance, so that the faint, singular signal they are hunting for can finally be heard. This isn't just science, it is a form of cosmic archaeology, where we are sifting through mountains of modern static to find the precious, ancient relics hidden beneath. Consider the monumental challenge of measuring the mass of a neutrino. We know these ghostly particles have mass because they oscillate, but pinning down their absolute weight is a Herculean task. The strategy isn't to catch one and put it on a scale. It's to study the energy distribution of particles emitted when another particle decays. The Katrin experiment in Germany is a masterpiece of this approach. It uses a giant, ultra-high-precision spectrometer the size of a house to study the beta decay of tritium. As tritium decays, it emits an electron and an anti-neutrino. The maximum energy that electron can have is directly stolen from the neutrino. If the neutrino has no mass, the electron gets a full, predictable share. But if the neutrino has even a tiny mass, it takes a little bit of that energy for itself, and the highest energy electrons will be ever so slightly less energetic. Katrin isn't measuring a signal, it's looking for the absence of a signal at the very end of an energy spectrum. It must control the temperature of its source with incredible stability, shield against the faintest magnetic fields from the Earth itself, and operate in an ultra-high vacuum to prevent any stray collisions. All of this to detect a minuscule kink in a graph that reveals a mass so small it is measured not in kilograms, but in electron volts, a unit billions of times smaller. The hunt for proton decay demands an even greater scale and an even deeper patience. Super Kamiok, and in Japan, a colossal tank filled with 50,000 tons of ultra-pure water, buried a kilometer under a mountain, is the ultimate sentinel waiting for a single, never-before-seen event. The theory suggests that a proton might decay into a positron and a neutral pion with a lifetime of around 10 to the 34 years. To have a chance of seeing even a handful of these decays per year, you need a simply unimaginable number of protons under observation. Super K contains about 10 to the 34 protons in its water. Its walls are lined with over 13,000 incredibly sensitive eyes photomultiplier tubes that wait in total darkness for the telltale flash of Cherenkov radiation that would be produced by the decay products of a single dying proton. The experiment must be buried deep underground to shield it from the constant rain of cosmic rays that would create a blinding background noise. Researchers have waited for decades, sifting through data, and so far the proton has not betrayed its secret. This null result is itself a profound discovery, ruling out simpler theories and pushing the predicted lifetime to even more extreme values, guiding theorists toward more nuanced models of grand unification. These colossal efforts are just the beginning. The next generation of experiments is already rising from the depths. The Deep Underground Neutrino Experiment, or DUNE, will use a beam of neutrinos fired from Fermilab in Illinois to a massive detector in South Dakota, 1,300 kilometers away. Its far detector will be filled with 70,000 tons of liquid argon, a medium so pristine that it can record the exquisite details of a neutrino interaction in three-dimensional detail, like a microscopic bubble chamber the size of a cathedral. Meanwhile, in Japan, the Hyper-Kamiok project is building a detector that will hold a staggering 260,000 tons of water, more than 5 times the volume of Super K, increasing its proton count and its sensitivity to a vanishingly small decay rate by an order of magnitude. These projects are not just bigger, they are smarter, employing advanced machine learning algorithms to sift through the petabytes of data they will generate, searching for patterns too subtle for the human eye to ever discern. This drive for precision isn't confined to particle physics. It echoes through the history of science, like the elegant torsion balance used by Laurent Ertwers in the late 19th century. His goal was to test the equivalence principle, the idea that gravitational mass and inertial mass are identical, a cornerstone of Einstein's general relativity. Ertwers hung 2 different objects on a delicate rod suspended by a thin wire. If gravity pulled on them differently, the rod would twist. The effect he was looking for was vanishingly small, requiring him to isolate his apparatus from vibrations, temperature changes, and even the magnetic influence of the Earth. His experiment was so precise that it confirmed the equivalence principle to within a few parts in a billion, a stunning feat for its time. Today, experiments like microscope in space are testing this same principle to 1 part in a trillion, because any tiny deviation could shatter our understanding of gravity and point toward new dimensions or forces. This relentless pursuit of smaller uncertainties, of more decimal places, is the engine of fundamental discovery. It is a testament to human collaboration and ingenuity, where teams of thousands, from engineers to theorists, work for decades, not for a quick result, but for the chance to hear the universe's quietest secrets, one infinitesimal number at a time. So where does this relentless pursuit of precision leave us? After journeying from the quantum foam to the cosmic horizon, we are faced with a set of numbers so precise and so pivotal that they demand an explanation beyond mere equations. We are pushed from the realm of physics into the domain of philosophy, forced to ask what these values truly mean for the nature of reality itself. Do they point to a grand designer, a cosmic architect who deliberately set the dials to allow for life and consciousness? This is the argument from fine-tuning, a modern version of the watchmaker analogy that suggests the universe's exquisite balance is evidence of intentional creation. It is a powerful and intuitively satisfying conclusion for many, offering a narrative of purpose and meaning woven into the fabric of existence. Yet for others, this answer feels like a retreat from scientific inquiry, an appeal to an unexplained explainer that ultimately halts the search for a deeper physical cause. This is where the work of thinkers like Brandon Carter becomes essential. Carter, a brilliant astrophysicist, formalized what is known as the anthropic principle. In its simplest form, it is a statement of observational selection bias. We should not be surprised to find ourselves in a universe compatible with our existence, because we could not possibly observe one that is not. The constants are what they are because if they were significantly different, we would not be here to measure them. This is not an explanation for why the constants have their values. It is an explanation for why we observe the values that we do. It reframes the question from, why is the universe so perfectly tuned for life, to, what must the universe be like for observers to eventually arise within it? This shift is profound. It turns the fine-tuning problem from a potential argument for design into a constraint that any ultimate theory of the universe must satisfy. Carter's principle doesn't solve the puzzle, but it gives us a crucial logical tool for navigating it, forcing a humility about our place in the cosmos and the data we collect. The anthropic principle finds its most dramatic expression in the multiverse hypothesis. If our universe is just one bubble in a vast, perhaps infinite, cosmic foam, each with its own random set of physical constants, then the mystery of our lucky numbers vanishes. In an infinite multiverse, every possible combination of constants will be realized an infinite number of times. We simply find ourselves in one of the rare habitable universes, a statistical inevitability rather than a miraculous accident. This idea is powerfully compelling to many physicists because it replaces the need for a designer with a mechanism of pure chance on an unimaginable scale. Yet it also presents a profound philosophical challenge. If the multiverse is real, then our universe is rendered utterly mundane, its properties stripped of any special significance. The quest for a unique, fundamental theory that explains why the constants must have their values is abandoned in favor of a cosmic lottery where our ticket just happened to win. This can feel, to some, like a cop-out, a surrender of the traditional goal of physics to find elegant, necessary laws. We are left to wonder if this is a genuine breakthrough in our understanding, or merely a sophisticated way of telling ourselves that some questions are beyond answering. An even more radical perspective comes from Max Tegmark and his mathematical universe hypothesis. Tegmark proposes that our universe isn't just described by mathematics, it is mathematics. In this view, every mathematically consistent structure exists as a physical reality. Our universe is one such structure, and the apparent constants of nature are simply the specific parameters that define this particular mathematical object. There is no deeper why. The universe exists because it is mathematically possible. This idea pushes the multiverse concept to its ultimate limit, suggesting a reality of literally infinite diversity, most of which would be utterly incomprehensible to us. Tegmark's hypothesis is breathtaking in its scope and austerity. It eliminates the need for any external entity or initial condition, grounding existence squarely in the abstract, timeless realm of mathematics. It suggests that the small numbers we obsess over are not clues to a larger physical reality, but to a deeper mathematical one. The order we perceive is not imposed from the outside. It is the inherent structure of the logical system in which we are embedded. These competing visions, design, anthropic selection, multiverse, mathematical necessity, are not just academic exercises. They fundamentally shape how physicists approach their work and what they consider a satisfactory explanation. They influence which theories are pursued, which experiments are funded, and how data is interpreted. The search for meaning in physics is inextricably linked to our interpretation of these small numbers. Are we reading too much into them, imposing a human narrative of purpose on a cold, impersonal cosmos? Or are they the genuine fingerprints of a deeper layer of reality, the only clues we have to guide us toward a truer understanding? Perhaps the answer lies not in choosing one vision over the others, but in recognizing that each reveals a different facet of a truth that is ultimately beyond our current comprehension. The small numbers stand as permanent invitations to wonder, challenging us to look beyond the equations and never stop asking what it all means. So we've journeyed through a cosmos filled with inexplicable values, from the profound weakness of gravity and the ghostly lightness of neutrinos to the eerie silence of dark matter and the impossible precision of the universe's first moments. Each of these small numbers on its own is a fascinating puzzle, but when we step back and look at them together, a breathtaking possibility emerges. What if they aren't isolated quirks at all? What if they are all interconnected clues, scattered pieces of a single grand puzzle, each one pointing toward a larger, hidden reality that unifies all of physics? Think of it like this. Imagine finding a handful of beautifully crafted, intricate keys, each one unique and seemingly unrelated. You could admire each key on its own, marveling at its design. But the real revelation comes when you realize they all fit into different locks on the same enormous door. The tiny value of the cosmological constant, the vast hierarchy between particle masses, the inexplicable smallness of the strong CP parameter, these aren't separate problems. They are all different locks, and behind that door lies a unified theory of everything, a framework where these numbers are not arbitrary inputs but natural outputs emerging from a deeper, more elegant set of principles. What could those principles be? For many physicists, the most compelling candidate is symmetry. Throughout the history of physics, every time we've discovered a deeper symmetry in nature, a rule that says the laws of physics look the same from a different perspective, we've made a monumental leap forward. The equivalence of all inertial observers led to special relativity. The symmetry of local gauge invariance gave us the standard model. It's widely believed that the next great leap will come from a symmetry that incorporates gravity into the quantum world, a supersymmetry or perhaps a conformal symmetry that treats all scales of energy equally. In such a theory, the small numbers we struggle to explain might simply vanish. They would be forced to be zero or nearly zero by the unforgiving logic of mathematical consistency. The incredible fine-tuning wouldn't be a coincidence, it would be a requirement. The universe would have no choice but to be the way it is. This is the hopeful dream behind efforts to derive constants like the fine structure constant from first principles, to show that 1 divided by 137 isn't a random value but the inevitable outcome of a fundamental equation. Another powerful idea is that these small numbers are a direct consequence of our universe's geometry at the most fundamental level. In string theory and some approaches to quantum gravity, the three-dimensional space we experience is just a shadow. The true reality might involve extra dimensions curled into a complex shape, or a two-dimensional information boundary from which our world is projected, a hologram. In these visions, the values of our constants are not free parameters, but are determined by the specific way these extra dimensions are folded. The gravitational constant seems weak because gravity is diluted as it leaks into these other dimensions. The cosmological constant is small because our particular cosmic bubble has a geometry that almost, but not quite, cancels out the vacuum energy. The small numbers become a signature of the hidden architecture of spacetime itself, a cosmic ZIP code telling us where we live in a much larger landscape of possibilities. And that landscape brings us to the most expansive interpretation of all, the multiverse. If our universe is just one of a vast, perhaps infinite, number of universes, each with its own random set of physical constants, then the mystery of our small numbers evaporates. We do not live in a specially tuned universe, we live in a survivable one. In most universes, the constants are set to values that are disastrously large or small, leading to instantaneous collapse or eternal, featureless emptiness. But in a rare subset, by pure statistical chance, the numbers fall within the narrow window that allows for galaxies, stars, planets, and life. We find ourselves here not because this universe is special, but because it is the only kind of universe we could possibly observe. This idea transforms the question from why are the constants so small to what are the environmental conditions necessary for our existence. It's a Copernican revolution on the grandest scale, humbling yet profoundly explanatory. The most exciting part is that this isn't just philosophical speculation anymore, it's a research program. Scientists are actively looking for connections between these small numbers, searching for a hidden equation that might link them. Could the value of the cosmological constant be mathematically tied to the mass of the electron? Could the strength of the electromagnetic force be derived from the geometry of the extra dimensions? Every time an experiment like the Large Hadron Collider fails to find a predicted particle, or a deep space telescope reveals a new constraint on dark energy, it helps to carve away at the possibilities, guiding us toward the correct path. The persistent tension in measuring the Hubble constant might not be an error, but a signal, a faint tremor indicating that our standard model of cosmology is missing a crucial piece, perhaps one that connects the very small to the very large. This is the beautiful synthesis. The smallest numbers in physics are not annoying imperfections in our theories. They are the very threads that, when pulled, may unravel the entire tapestry of reality to reveal the grander design woven beneath. They are the universe's way of whispering its deepest secrets, urging us to look beyond the obvious and to imagine a reality far more wonderful and interconnected than we ever thought possible. The journey to understand them is far from over, but each small number is a beacon, guiding us toward a future where the largest truths are finally revealed. So we've traveled from the quantum foam to the cosmic horizon, tracing a path of clues written in the universe's most inexplicable numbers. We've seen how the gravitational constant's profound weakness hints at hidden dimensions, how the cosmological constant's impossible smallness might point to a vast multiverse, and how the ghostly mass of a neutrino could be a whisper from particles trillions of times heavier. These aren't just isolated curiosities, they are interconnected puzzles, each one a piece of a much larger picture. The fine-tuning of forces for life, the staggering hierarchies between energy scales, and the persistent experimental tensions all sing the same song. Our current understanding of reality is incomplete. These small numbers are the universe's way of nudging us, of suggesting that behind the curtain of our everyday experience lies a deeper, more unified, and more spectacular reality waiting to be discovered. Whether that reality is a landscape of countless universes, a higher dimensional architecture, or a web of undiscovered symmetries, the journey to find it is the most exciting adventure in human thought. It challenges us to rethink everything we know about existence, from the nature of nothingness to the origin of everything. As Albert Einstein once marveled, the most incomprehensible thing about the universe is that it is comprehensible. The fact that we can even begin to probe these mysteries, to measure these tiny numbers and ask these profound questions, is a testament to the power of human curiosity. So keep wondering, keep questioning, and stay fascinated by the cosmos's deepest secrets. If you enjoyed this deep dive into the clues hidden in reality's code, make sure to subscribe and hit the bell for more journeys to the edge of understanding. And let us know in the comments, which of these small numbers do you find the most mysterious? Is it the eerie value of the cosmological constant, the ghostly mass of the neutrino, or something else entirely? The conversation is just beginning. Thanks for watching.